We live inside a bubble. It is invisible, enormous, and absolute. This bubble is not made of glass or matter, but of light itself. Beyond its edge, the universe continues filled with galaxies, stars, and perhaps infinite wonders. Yet we cannot see them, cannot reach them, cannot even prove they are there. The edge of our bubble is the farthest that light has had time to travel since the birth of everything. It is called the observable universe, and it is the wall that mocks every ambition we have to explore. The paradox is immediate. The universe may be infinite, but to us it is bounded. On Earth, explorers once faced oceans that seemed endless horizons that promised new worlds and frontiers that eventually yielded to courage and sail. But in space, our horizon is not a distance we can cross. It is a barrier set by the speed of light, a speed that no machine or mind can overtake. We are like sailors trapped on an island watching waves that never carry us closer to the shore beyond. Let us for a moment imagine that we dare to attempt the impossible. What would it take to travel to the other side of the universe? Could we build a ship capable of outrunning time itself? Could we fold the fabric of space-time into a bridge? Or could there be a loophole hidden in the strange rules of the quantum world? These are not idle questions. They cut to the heart of what we know and what we cannot yet know about reality. The first challenge is simple to state but impossible to solve. Nothing, according to Einstein's theory of relativity, can move faster than light in a vacuum. A beam of light travels at 300,000 kilometers per second, and that is the ultimate speed limit. The faster we accelerate toward it, the harder the laws of physics push back. Mass increases, energy demands soar, and time itself begins to distort. For a traveller moving near the speed of light, moments stretch and twist. A journey that seems to take centuries from the outside might pass in a handful of years for those aboard. This effect, called time dilation, is not science fiction. It has been measured with clocks on airplanes, with satellites orbiting Earth, with particles racing in accelerators. So in principle, yes, we could build a vessel that approaches the speed of light, and for its crew, entire galaxies might slip by within a lifetime. But here lies the cruel twist. The universe itself is expanding. Space is not a stage where actors move, but a fabric that stretches. Galaxies at the edge of our sight are receding faster than light itself, carried away by the expansion of space-time. No matter how fast we travel, the finish line runs ahead, always out of reach. The other side of the universe is not a fixed destination. It is a moving horizon, like a mirage that recedes as we chase it. This realization is devastating, but it does not end the story. If speed cannot take us there, perhaps geometry can. Einstein's equations, written more than a century ago, describe how matter and energy bend the shape of space-time. Under the right conditions, space-time can fold back on itself, creating shortcuts we call wormholes. Imagine a tunnel carved through the fabric of reality, linking two distant regions as easily as a subway links neighborhoods of a city. In theory, stepping through one end could deliver you instantly to the far side of the cosmos. It sounds like magic, but it is mathematics. The equations admit the possibility, yet they also demand a price. To hold a wormhole open to prevent it from collapsing into nothing requires something nature may not provide. Exotic matter with negative energy density. This is not ordinary material. It is not fuel rock or plasma. It is matter that would behave in ways utterly alien, pushing instead of pulling, repelling instead of attracting. Without it, the tunnel collapses before anything can pass through. The hunt for negative energy is not hopeless. A faint whisper of it has already been glimpsed in the laboratory, in an effect called the Casimir force. Place two metal plates very close together in a vacuum and quantum fluctuations push them inward. The vacuum itself exerts a pressure hinting that energy can be less than zero, but the amounts are vanishingly small, far from what would be needed to stabilize a cosmic passage. So once again the dream retreats. We are left stranded inside our bubble, tantalized by the mathematics of wormholes, denied by the physics of matter. And yet, just as our despair deepens, a new possibility emerges from the smallest scales of all. Quantum mechanics does not treat space-time as smooth and continuous. At the tiniest dimensions, reality froths and foams. Space itself may flicker, twisting into bubbles, tunnels, and fleeting connections. Perhaps the universe is already filled with wormholes, microscopic, unstable, vanishing before anything can enter. If that is true, then the cosmos is riddled with invisible doors, locked but not destroyed. The challenge is not their existence, but our ignorance of how to use them. Could an advanced civilization reach into the quantum foam, seize a tiny wormhole, and stretch it like a balloon until it became a gateway. Could that be the path to the far side? We do not know. We cannot know yet. What we do know is that the universe has a habit of tempting us with paradoxes. It shows us the key in equations, then hides it in physics. It whispers that there may be roads across infinity, then bars them with conditions we cannot meet. And so we are left on the edge of mystery, peering outward from our fragile bubble of light. And that is where our journey truly begins. At the smallest scales of existence, the smooth stage of space-time dissolves into chaos. Physicists call it the quantum foam, a restless sea where uncertainty rules and the very geometry of the cosmos flickers like static. To us the vacuum looks empty, but emptiness is an illusion. Virtual particles burst into being and vanish almost instantly. Energy fluctuates, distances blur, and causality itself begins to tremble. Here in this microscopic storm, wormholes may already exist. Not the massive tunnels imagined in science fiction, but tiny unstable channels flickering into and out of existence in less than a heartbeat. They are the scars of uncertainty forming and collapsing faster than light can cross them. For us, they are useless, but to nature they are reminders that reality is not fixed, that space and time may be far stranger than our senses allow. The dream then is to catch one. Imagine capturing a microscopic wormhole before it vanishes, stabilizing it with exotic energy, and inflating it until it could swallow a starship. The idea is audacious, almost absurd, yet not forbidden by mathematics. The physicist Kip Thorne once speculated about such possibilities, suggesting that wormholes might be engineered if we could manipulate quantum fields with enough precision. It would be like grabbing a bubble from boiling water and freezing it before it bursts. If that could be done, the bubble could grow into a tunnel large enough to step through. But theory punishes imagination with cost. To hold open such a passage, negative energy must be supplied in quantities far beyond anything we can generate. The Casimir effect offers a glimpse, but it is the faintest whisper of what would be needed. The gulf between laboratory trickles and cosmic rivers is vast, perhaps uncrossable. Our most advanced particle accelerators barely scratch the surface of what would be required. Still, the idea refuses to die. The existence of dark energy itself, an unknown force driving cosmic expansion, hints that the universe is capable of producing negative pressure on unimaginable scales. Could there be a link between the engine of cosmic acceleration and the exotic matter demanded by wormholes? If dark energy is the backdrop of the universe, then perhaps it is the very ingredient we need hiding in plain sight. We just do not yet know how to shape it. And this leads us to another paradox. The same dark energy that might permit us to construct shortcuts is also the force pulling the universe apart, carrying galaxies beyond our reach. It is both our captor and our potential liberator. Harnessing it would mean taming the very expansion that imprisons us a feat, that makes the construction of rockets or even fusion engines seem trivial in comparison. Suppose, though, that we succeed. Suppose some civilization, human or otherwise, manages to master the quantum foam inflate wormholes and lace the cosmos with tunnels. The far side of the universe could then be a step away. But the story does not end with triumph, for relativity is not done with us. Wormholes are not just passages through space, they are passages through time. A stable wormhole manipulated in the right way could become a time machine. If one mouth is accelerated near the speed of light and then returned, the two ends become unsynchronized by time dilation. Enter one end and you could emerge not only elsewhere but elsewhen. The laws of physics appear to allow this. The implications are staggering. The paradoxes unfold instantly. If I step through and arrive before I leave, can I prevent myself from ever travelling? If so, who then emerges? Such questions gnaw at causality, shredding the idea of consistent history. Physicist Igor Novikov proposed a resolution. Perhaps the universe enforces consistency, allowing only loops where the past cannot be changed. But Stephen Hawking suggested something harsher. A chronology protection principle, an invisible safeguard preventing time machines from ever forming. According to him, the universe itself despises paradoxes and would erase them before they arise. If Hawking is right, then every attempt to stabilize a wormhole would collapse under the weight of quantum fluctuations, destroying the machine before it could be used. Time travel would remain a mirage, always visible in theory but forbidden in practice. If Novikov is right, then time travel might occur, but only in ways that lock us into unbreakable loops, robbing us of freedom to change the past. Either way, the dream of using wormholes to cross the cosmos is shadowed by consequences we may not be willing to face. To reach the other side of the universe, we may be forced to tamper with time itself, and time is a thread that resists being pulled. Yet the paradox does not extinguish wonder. Instead, it sharpens it. If the universe teases us with the possibility of shortcuts, even impossible ones, then perhaps the deeper message is that we have not yet uncovered the full set of rules. Physics is not finished. Relativity and quantum mechanics are masterpieces, but they are incomplete. Somewhere hidden in the fabric of reality is a deeper law that unites them. Until we find it, the road to the far side remains closed. And so we stand at a threshold. On one side is everything we know, rockets' relativity expansion horizons. On the other side is everything we cannot yet imagine. Wormholes' quantum gravity, perhaps new dimensions. Between them lies ignorance, the most formidable barrier of all. Imagine for a moment that we somehow bypass all the obstacles. We discover exotic matter, stabilize wormholes, and create a network of tunnels spanning the universe. The dream is realized. The other side is within reach. But relativity does not surrender so easily. Inside the equations lurks a trap, one that makes even victory taste like defeat. Wormholes, no matter how carefully engineered, are not gentle places. The gravity that shapes them is ferocious, curving space-time so sharply that even the slightest imbalance can destroy the tunnel. Any traveller who dares to enter risks being torn apart by tidal forces stretched into threads of atoms in a process called spaghettification. What science fiction depicts as smooth corridors of light might in reality be chaotic maelstroms of distortion, with energy densities so extreme that no material we know could survive them. Even worse, wormholes are unstable. According to calculations, they collapse faster than light could travel through them. By the time a ship even begins its journey, the passage has already pinched shut. The only way to hold it open is to continuously feed it negative energy in amounts that dwarf the output of entire stars. It is like trying to keep a bridge from crumbling by pouring oceans into its foundations every second. And if somehow the wormhole remains open, new dangers emerge. Closed time-like curves pass through space-time that loop back into the past are a natural consequence. Step through the wrong way and you may arrive before you left. Cause and effect unravel, leaving paradoxes in their wake. The universe, it seems, resists being cheated. This has led some physicists to a sobering conclusion. Wormholes may exist, but not for travel. They may form and vanish in the quantum foam or lurk inside black holes, but they remain out of reach like forbidden passages glimpsed in dreams. The mathematics teases us, but the physics denies us. Yet the dream does not end here because the universe has other secrets. Black holes themselves, those engines of destruction, might hint at ways across the cosmos. When Einstein and Nathan Rosen first explored their equations in the 1930s, they discovered that the mathematics of a black hole naturally connected to a white hole, a hypothetical object that ejects matter instead of swallowing it. Together they formed what became known as the Einstein-Rosen bridge, a wormhole born not from speculation but from the structure of relativity itself. If such bridges exist, then falling into a black hole might not be the end but the beginning of a journey. On the far side, matter could re-emerge from a white hole in another region of space, perhaps even another universe. It is a vision at once terrifying and exhilarating. The most violent objects in the cosmos transformed into cosmic gateways. But nature does not seem to play along. Real black holes are not eternal mathematical constructs. They form from collapsing stars, and their interiors are not stable bridges but singularities points. Where density becomes infinite and known physics breaks down. Anything that crosses the event horizon is doomed, not transported. The bridge collapses before it can be crossed. Still, the idea lingers. In the mathematics of relativity, bridges are possible. In the harsh reality of astrophysics, they are not. But between these two lies a gap, and in that gap might be the key. What if black holes are not merely destructive? What if under conditions we do not yet understand they really are connected to something else? This speculation gains fuel from the mystery of information. According to classical physics, anything that falls into a black hole is lost forever. But quantum theory insists that information cannot be destroyed. This contradiction, the black hole information paradox, has haunted physics for decades. If information does escape, then perhaps black holes are not tombs but gateways leaking clues to a larger reality. Could it be that the other side of the universe is hidden not across vast distances, but within the very objects we fear most? Could black holes be doors disguised as prisons? If so, then the path to the far side may not lie in outrunning expansion or bending geometry, but in understanding what truly happens beyond the event horizon. And that question, the fate of information, the reality of black hole interiors, leads us to the frontier of modern physics. To answer it, we must confront quantum gravity, the long-sought theory that unites relativity and quantum mechanics. Without it, our visions remain speculation. With it, the truth may finally be revealed. The far side of the universe might not be a place we can sail to like an ocean. It might be hidden in the very structure of space and time, waiting for us to decipher the language of reality itself. And so the journey continues deeper into the paradox of horizons. When we gaze into the night sky, we imagine the stars and galaxies as if they are arranged on a vast cosmic map. But this map is deceptive. Every point of light we see is not what it is, but what it was. Light takes time to travel, and the farther we look, the older the message becomes. The most distant galaxies appear to us not as they are today, but as they were billions of years ago. The deeper we peer, the younger the universe looks, until eventually we reach a time when galaxies had only just begun to form. The James Webb Space Telescope has allowed us to push this vision to its limit. With its infrared eyes, Webb peers through cosmic dust and across billions of light years, revealing galaxies from a time less than 1 billion years after the Big Bang. What it sees is astonishing. Instead of a sparse cosmos of tiny fragile structures, Webb has found massive galaxies, brilliant with stars and supermassive black holes lurking at their hearts. These should not exist so early, not according to our models. Their presence suggests that either galaxies grow faster than we thought, or that our understanding of cosmic evolution is incomplete. But even Webb has a limit. Beyond a certain distance, light cannot reach us at all, no matter how powerful our instruments. This distance is set not by our technology, but by the age of the universe and the speed of light. We cannot see beyond the cosmic horizon because there has not been enough time for that light to arrive. The other side is hidden behind time itself. This horizon is not just a matter of sight, it is a matter of causality. Beyond it, events are disconnected from us. No signal, no ship, no message could ever cross the gulf. Those regions might as well belong to another reality, forever sealed away. And yet they exist. Their gravity tugs faintly on what we can see. Their structures shape the universe indirectly, but they remain beyond our grasp. It is here that the mystery deepens. If the universe is infinite, then the other side is simply more of the same galaxies stretching endlessly, structures repeating without end. But if the universe is finite, then the other side might not exist in the way we imagine. The cosmos could wrap back on itself like the surface of a sphere, travel far enough in one direction, and you might return from the other just as a ship circling Earth arrives where it began. In such a universe, the other side is not a distant land, but the very place you started approached from behind. Astronomers have searched for evidence of such curvature. They study the cosmic microwave background, the afterglow of the Big Bang, mapping its faint ripples in exquisite detail. If the universe were curved like a sphere or a donut, patterns would repeat, circles in the sky would match, echoes would appear. So far, the evidence suggests that space is flat or nearly so, extending without curvature. But flat does not mean infinite. It may still be finite, like the surface of a vast sheet folded in ways we cannot see. If this is true, then the other side of the universe is not unreachable. It is an illusion. There is no edge to cross because every path eventually loops back. The horizon is not a boundary, but a trick of perspective created by the marriage of light and time. Yet there is another possibility stranger still. Our universe may not be the only one. The equations of inflation, the rapid expansion that occurred fractions of a second after the Big Bang, suggest that our bubble of reality may be just one among countless others. If so, the other side might not be across space, but across universes. Parallel realms could exist beyond our horizon, each with different laws of physics, different histories, perhaps even different versions of us. If wormholes or quantum fluctuations connect these realms, then the other side of the universe is not just unreachable, it is unrecognizable. We may expect galaxies and stars, but instead find realities where gravity repels, where time flows differently, where matter itself does not exist. The other side might not be the destination we imagine. It might be alien beyond comprehension. And this leaves us with a profound question. What do we really mean by the other side? Is it simply more galaxies hidden beyond our horizon? Or is it an entirely different order of reality, a multiverse of infinite variation? The answer is unknown. but the pursuit itself reshapes our understanding, turning the unreachable into a mirror of our ignorance and our curiosity. The other side of the universe is less a place and more a challenge, a reminder that we have only just begun to decipher the code of existence. And as we stand on this horizon staring outward into the unknown, we are faced with the possibility that the most profound discoveries lie not across space, but in the laws that govern it. If the other side of the universe is hidden behind horizons, then perhaps the path to it lies not in distance, but in understanding those horizons themselves. One of the strangest discoveries of modern cosmology is that horizons are not merely observational limits. They are physical boundaries woven into the laws of reality, shaping what is possible and what is forbidden. Consider the event horizon of a black hole. It is not a surface of matter, but a boundary in space-time. Cross it and escape becomes impossible. Information is trapped, light itself cannot return, and to outside observers, time appears to freeze. The black hole event horizon is a cousin of our cosmic horizon, both defined by light and the inability of signals to cross. In one case, gravity pulls so strongly that escape is denied. In the other, expansion carries galaxies away faster than light can bridge the gap. In both, the horizon is a point of no return. But unlike the event horizon of a black hole, the cosmic horizon is not absolute for everything. Galaxies beyond it continue to exist. Their light may never reach us, but their gravitational influence can still shape the universe. In fact, subtle patterns in the cosmic microwave background suggest that what lies beyond our horizon has left its fingerprints. The unseen still affects the seen like a ghost pressing against the fabric of our reality. This raises a provocative idea. What if the far side of the universe is not truly cut off but only hidden? Could we use something other than light to glimpse it? Gravitational waves, ripples in space-time itself offer such a possibility. Unlike light, they interact so weakly with matter that they can cross barriers that photons cannot. Detectors like LIGO and Virgo have already caught these whispers from colliding black holes and neutron stars. In principle, gravitational waves from the earliest moments of the Big Bang could carry information from beyond the light horizon, from times and places we thought forever unreachable. If we could detect such primordial waves, we might glimpse a snapshot of the universe before light itself could travel freely. It would not be the far side in space, but the far side in time. And perhaps hidden in their delicate vibrations lies evidence of what lies beyond our bubble. Still, the gulf remains. Even if information leaks through, even if subtle signals betray the presence of distant realms, travel is another matter. To physically cross is to fight expansion itself. Here we encounter one of the most unsettling truths of cosmology. The universe is not just expanding, it is accelerating. Galaxies are not only receding, they are speeding up. The more distant they are, the faster they run. Beyond a certain threshold, they vanish forever, receding faster than light. This is not a temporary state. It is the long-term fate of our cosmos, driven by the mysterious force we call dark energy. Dark energy is perhaps the most baffling discovery of the last century. It makes up nearly 70% of the universe, yet we do not know what it is. We know only what it does. It pushes relentlessly, counteracting gravity, stretching the fabric of space. Without it, the expansion of the universe would slow. With it, the expansion accelerates, turning horizons into permanent barriers. The irony is painful. Dark energy imprisons us within our observable bubble, sealing the far side forever. And yet it may also hold the key to crossing it. If we could understand its nature, manipulate it, even harness it, we might gain control over space-time itself. Dark energy is both jailer and potential liberator, but at present it remains a mystery, perhaps the greatest in all of physics. This leaves us with a haunting vision of the future. As billions of years pass, galaxies slip beyond our horizon one by one. The night sky grows emptier. Eventually only our own local group of galaxies will remain bound together by gravity while the rest vanish into darkness. To future astronomers, the universe will appear small, finite, isolated. They will not even know that other galaxies once existed. The far side will be erased not only from view, but from memory. We living now are in a privileged position. We can still see the great expanse, still measure the expansion, still sense the enormity of what lies beyond. We are perhaps the only generation of cosmic observers who can grasp the scale of the universe in its fullness, before most of it disappears forever beyond the horizon. And so the question burns brighter. Could we find a way to cross the gulf before it is too late? Could we outwit dark energy, tame the expansion, or cheat the laws that confine us? The answer remains hidden, but the urgency grows. The horizon is not only a mystery, it is a countdown. If horizons limit us, then perhaps the solution is not to cross them, but to change them. The idea sounds impossible, almost arrogant, yet it emerges naturally when we ask a daring question. What if we could reshape space-time itself? In 1994, physicist Miguel Alcubierre proposed a radical concept now known as the Alcubierre drive. The idea is simple to describe, yet staggering in implication. Instead of pushing a ship through space faster than light bends space around the ship, compress space-time in front, expand it behind, and let the vessel ride a wave of distorted geometry. Inside its bubble, the ship would never exceed light speed relative to its immediate surroundings, keeping relativity intact. But to an external observer, the bubble itself could move faster than light, carrying its contents across unimaginable distances in short spans of time. This concept became famous as the warp drive, echoing science fiction dreams. But unlike fiction, Alcubierre's mathematics were real, drawn from Einstein's equations themselves. The drive is not forbidden by relativity. The catch, of course, is the same ghost that haunts wormholes: negative energy. To create and sustain the bubble, one must manipulate exotic matter on scales beyond comprehension. Early estimates suggested that the energy equivalent of the entire observable universe might be required to move a single ship. Later refinements reduced the number, but even the most optimistic versions still demand resources far beyond anything humanity could muster. Yet the vision endures because it reshapes the problem. Instead of breaking the light speed limit, we avoid it. Instead of chasing galaxies as they flee, we bend the track beneath us. If negative energy can be mastered, then the far side of the universe is no longer a forbidden dream. It becomes a reachable destination. The challenges are immense, but the concept carries an important lesson. Horizons are not immovable walls. They are features of space-time, and space-time is malleable. If we learn to sculpt it, we may discover paths where none exist today. But bending space may not be the only path. Theories of higher dimensions suggest that our universe might be just one slice of a larger reality. String theory, for instance, describes the fundamental particles not as points, but as vibrating strings whose harmonies require extra dimensions curled up beyond our perception. If those dimensions can be unfolded or accessed, then shortcuts through them might bypass the limitations of our three-dimensional space. In such a scenario, the far side of the universe could be only a small step away in a higher dimensional landscape. These ideas remain speculative, untested, and controversial. Critics argue that without experimental evidence, higher dimensions and warp drives are nothing more than mathematical fantasies. Yet history has shown that imagination often precedes discovery. Once black holes were dismissed as absurdities of theory. Today we image their shadows with telescopes spanning the Earth. Once gravitational waves were considered too faint to detect. Today they are recorded routinely. What seems impossible in one century may become routine in the next. Still, there is a danger in hope. For every breakthrough that reshapes our view, countless dreams remain unrealized. Anti-gravity, perpetual motion, faster than light communication, all have been imagined and none have been achieved. The cosmos is not obligated to yield to our desires. The other side of the universe may remain forever hidden no matter how clever our theories. And yet to abandon the pursuit is to betray curiosity itself. The impossible challenges us not because they promise success, but because they reveal the boundaries of what is known. In probing those boundaries, we discover more than answers. We discover who we are, beings who refuse to accept walls without first testing them. Perhaps one day, long after our civilization has evolved beyond recognition, descendants of our species or minds we cannot even imagine will wield the tools to manipulate space-time as easily as we now sail oceans. To them, horizons may be mere inconveniences, the far side of the universe, no more distant than another city is to us. Whether or not that day comes, the seeds of it lie here in our restless need to ask if the journey is possible. The universe is not static. It is a dynamic arena, restless and evolving. Galaxies form stars, ignite planets, coalesce black holes, devour, and everywhere in between, space itself stretches. This expansion is the great thief of horizons, stealing galaxies from our view one by one. And yet it is also the great sculptor shaping the very fabric we hope to traverse. To talk about reaching the other side of the universe without confronting cosmic expansion is to ignore the stage upon which the drama unfolds. When Edwin Hubble first discovered in the 1920s that galaxies were receding from us, the picture was startling but simple. Space was stretching, and the farther away something was, the faster it fled. At first, it seemed that gravity might slow this expansion. Perhaps one day the universe would halt, then reverse collapsing into a fiery end known as the Big Crunch. But in the late 1990s, new evidence shattered that expectation. Observations of distant supernovae revealed that the expansion is not slowing down. It is accelerating. Some unknown force, dubbed dark energy, is driving galaxies apart at an ever-increasing pace. This changes everything. With acceleration, horizons are no longer temporary. They become permanent. Beyond a certain distance, galaxies are carried away faster than light, forever disconnected. The more time passes, the closer that horizon creeps. Eventually, only the small cluster of galaxies bound to our own will remain visible. All else will fade into darkness. For those who dream of travel, this is devastating. No matter how advanced a starship we build, no matter how clever our engineering, the expansion ensures that the vast majority of the universe will slip beyond our reach. The finish line is not just far away, it is moving faster than we can ever hope to chase. The far side is receding into a void we cannot conquer, and yet there is a strange comfort hidden here. If the horizon is set by the speed of light and the power of expansion, then it is not a fixed wall but a dynamic boundary. It defines what is possible now, not what will be possible forever. If we could one day manipulate dark energy itself, perhaps we could rewrite the rules of expansion. The far side would not vanish, it would reappear. This is not pure fantasy. We already know that the universe is governed by quantum fields, invisible scaffolds that fill all of space. Dark energy may be one such field. If so, it is not unreachable. It is part of the very vacuum between atoms woven into the same reality we inhabit. We may not yet know how to touch it, but its fingerprints are everywhere. The challenge is not its existence, but our ignorance. There is another implication darker still. If dark energy grows stronger with time, then the expansion may not simply continue. It may accelerate without end, tearing galaxies apart, then stars, then planets, then even atoms in a final disintegration called the Big Rip. If that fate awaits, then travel to the other side of the universe is not just difficult, it is doomed. There would be no other side to reach, only fragments dissolving into the vacuum. But fate is not yet sealed. Our measurements of dark energy are still crude, our models still uncertain. For now, the evidence points to a constant, steady push. If that is true, then the universe will expand forever, cooling into heat death. A future of darkness, silence, and emptiness. The other side of the universe in that scenario becomes not a place but an absence. Still, in our age, we remain privileged. We live at a cosmic moment when the universe is vast and visible, when horizons stretch far and galaxies fill the sky. We can ask the question with wonder. What lies beyond? Future civilizations may never even know to ask. To them, the sky will reveal only isolation. The far side will be erased from history itself. That realization gives urgency to our quest. We are the observers standing at the edge of possibility, with tools powerful enough to glimpse the cosmos in its glory. If the universe is to teach us its secrets, it must be now before the curtain falls. And so, the dream of travelling to the other side is not just about exploration. It is about seizing a moment in cosmic history when the universe is still open to us. When we imagine the other side of the universe, we picture distant galaxies glittering in unreachable darkness. Yet the deeper puzzle is not distance, it is time. Every photon that reaches our telescopes is ancient, travelling across billions of years. The farther we look, the younger the universe appears, until eventually we confront the first light itself, the cosmic microwave background, a faint glow released when the universe was only 380,000 years old. Beyond that glow lies a fog through which no light can pass. This makes the far side of the universe not just invisible, but hidden behind the memory of creation. The cosmic microwave background is a wall painted with the fingerprints of the Big Bang. Its ripples reveal the seeds of galaxies, the distribution of matter, the geometry of space itself. But it is also a veil. We cannot peer beyond it with light, no matter how powerful our instruments become. And yet scientists have begun to dream of other messengers. Gravitational waves, those ripples in space-time itself, may carry information from earlier times. Unlike light, they pass unhindered through matter. If detectors sensitive enough could be built, they might capture echoes from the first instance of the universe. signals from an era when space-time expanded at a speed beyond comprehension during cosmic inflation. Such waves could reveal not only what lies behind the microwave background, but whether our universe is just one bubble among many. This is where the concept of the multiverse enters the stage. Inflation theory, while explaining the large-scale uniformity of the cosmos, also suggests that inflation may not have ended everywhere. Instead, it may continue eternally spawning countless bubble universes. If this is true, then the other side of our universe is not across space, but across realities. Our observable bubble is one among countless others, each potentially with different physical laws. In one, gravity might be stronger. In another, atoms might never form. In yet another, stars might burn out in moments, leaving darkness behind. Could we ever reach such realms? In principle, eternal inflation suggests that new universes form with horizons separating them. If wormholes or quantum fluctuations could link these bubbles, then travel between universes might be possible. But here the paradox grows deeper. The energy scales of inflation dwarf anything we can imagine far beyond the reach of engineering. To manipulate such forces would be to wield the power of creation itself. For now, the multiverse remains a mathematical whisper, a speculation born from equations and inference, not observation. Still, it teases us with possibility. If the far side of our universe is forever sealed, perhaps the real escape lies in leaving it altogether. Perhaps civilizations more advanced than ours, if they exist, have already walked this path, slipping between bubbles, migrating not across galaxies but across universes. If so, then our dream of crossing to the other side may already have been fulfilled elsewhere by minds we cannot imagine. But speculation carries its own danger. For centuries, humans believed the Earth was the center of everything. Later, we believed the Milky Way was the whole cosmos. Each time discovery humbled us. Perhaps the idea of crossing universes is simply the latest illusion, another projection of our longing for escape. Perhaps the truth is harsher. We are bound to our bubble forever, unable to reach even its edge, let alone what lies beyond. Yet the act of asking reshapes science. To test the multiverse, physicists hunt for subtle signatures, collisions between bubbles imprinted on the cosmic microwave background, unexplained anomalies in temperature patterns, or hints of exotic particles leaking from beyond. None have yet been confirmed, but the search itself drives technology forward, refining our instruments and sharpening our theories. Even failure brings progress. So the far side of the universe becomes both unreachable and indispensable. It is a paradox that fuels inquiry. We cannot travel there yet in seeking to understand it. We deepen our grasp of physics, time, and existence. The horizon is less a wall than a teacher. It denies us access but offers knowledge in return. If the multiverse tempts us with endless possibilities, black holes confront us with ultimate boundaries. They are cosmic prisons where gravity reigns supreme, swallowing everything that dares to cross their horizons. And yet, in the paradoxical way of the universe, these engines of destruction may also hint at escape routes. The equations of general relativity describe black holes with uncanny precision. They predict event horizons, singularities, and the warping of time itself. But tucked within the mathematics are structures called Einstein-Rosen bridges. These bridges connect a black hole to a hypothetical white hole, a mirror object that expels matter instead of devouring it. Together they form a wormhole, a tunnel through space-time. If stable, such a bridge could serve as a shortcut across the cosmos, perhaps even a path to the other side of the universe. The problem is stability. Real black holes are messy. They spin, they grow, they evaporate through Hawking radiation. None of them appear to host neat tunnels. The bridges collapse too quickly, pinching off before anything could pass through. The singularity at their heart shreds information, leaving us with paradoxes that pit relativity against quantum mechanics. And yet the very struggle to resolve these paradoxes may reveal something profound. Consider the black hole information problem. According to relativity, information that falls into a black hole is lost forever. But quantum theory insists information cannot be destroyed. Both theories cannot be correct, and reconciling them demands a deeper law, quantum gravity. Some proposals suggest that information leaks out in subtle ways encoded in Hawking radiation. Others argue that the interior of a black hole is connected to the outside through hidden geometry, perhaps even wormholes too small to detect. If so, then black holes are not prisons at all, but gateways revealing that space-time is more interconnected than we realize. There are even bolder ideas. The holographic principle suggests that all the information in a region of space can be described by data encoded on its boundary like a cosmic projection. If this is true, then our entire universe may be a hologram with reality itself, emerging from information inscribed on horizons. In such a picture, the other side of the universe may not be across distance, but across layers of information woven into the fabric of existence. These ideas are not proven, but they are more than speculation. They are attempts to solve contradictions, to bridge the gap between two of the greatest achievements of science, relativity and quantum mechanics. If successful, they may unlock not only the mystery of black holes, but the deeper nature of reality. And once again, horizons reveal their double role. They confine us, denying access, yet they also teach us, forcing us to probe deeper. A black hole's event horizon and the cosmic horizon may be different in scale, but they are united in spirit. Both are limits that hide the unknown, daring us to uncover it. Could the key to reaching the other side of the universe lie in understanding black holes? Perhaps. If they truly connect to other regions of space-time, then they may already be natural wormholes. We cannot survive the journey now, but maybe future physics will reveal ways to navigate their interiors. Or maybe the truth is even stranger, that black holes do not lead elsewhere in space, but elsewhere in reality, to domains we cannot yet describe. The irony is sharp. The darkest objects in the universe may hold the brightest clues to its structure. The very prisons we fear may be the doors we seek. To solve their riddle is to take a step toward the far side of the universe, not by crossing it, but by transforming our understanding of what side even means. And so the black hole, once a symbol of doom, becomes a symbol of possibility. If we dare to follow its mystery, we may discover that the other side is closer than we think, hidden not in distant galaxies, but in the geometry of reality itself. Every journey has a map, but in cosmology, the map itself is an illusion. When we chart the universe, we imagine a frozen snapshot, galaxies scattered like islands across a vast ocean. Yet the reality is stranger. What we see is not the universe as it is, but as it was. Every photon carries a delay, a record of ancient history. The farther we look, the deeper into the past we peer. This distortion means that our cosmic map is layered with time. Nearby galaxies show us the present, but the faintest smudges of light are fossils from billions of years ago. When we study them, we are not seeing neighbours across space, but ancestors across epochs. The other side of the universe is not just far away. It is elsewhere, hidden in the flow of time itself. This idea reshapes the meaning of travel. To reach the far side is not simply to cover distance, it is to cross ages. A voyage outward is a voyage backward, a trek not just across kilometres but across billions of years. The destination is not a place waiting for us, but a time that has already vanished. Even if we could step across instantly, what we would find is not the universe now, but the universe then. The James Webb Space Telescope has already given us glimpses of this temporal paradox. It has revealed galaxies so massive, so luminous, that they defy our models of early cosmic history. According to our theories, such giants should not have formed so quickly. Yet Webb shows them blazing less than 1 billion years after the Big Bang. They are ghosts of the young universe, messengers from an era that should not exist. If these galaxies can exist, then our understanding of time growth and structure may be incomplete. Perhaps matter clumped faster than we thought. Perhaps the laws of physics operated differently in the early universe. Or perhaps our models of cosmic expansion need revision. Whatever the answer, it reveals that the far side of the universe is not just about where we cannot go, it is about what we do not yet understand. There is a haunting implication here. If travel outward is travel backward, then to reach the true other side, the universe as it exists now, beyond our horizon, we would need to overtake time itself. We would need to arrive faster than light, faster than causality, into regions whose present is forever disconnected from ours. It is not simply forbidden, it is meaningless. For us, the other side does not exist as a simultaneous place. It exists only as a memory we cannot access. And yet this impossibility does not end the story. It deepens it. By studying the past, we infer the present. By mapping ancient light, we deduce what must be unfolding beyond our horizon. Through simulations, through mathematics, through observation, we reconstruct the unseen. The far side may remain hidden, but its influence leaks into what we can measure. This is where cosmology becomes detective work. We measure the faint anisotropies in the cosmic microwave background. We map the distribution of galaxies across billions of light years. We study the large-scale structure of the universe, the cosmic web of filaments and voids. From these clues we infer what lies beyond painting a picture of the unseen with equations and models. It is not direct travel, but intellectual travel, a journey across thought. As we pursue the far side of the universe, we inevitably confront the question of limits. Not technological limits, but fundamental ones. The universe is governed by laws that appear unbreakable. Yet throughout history, many of those laws have been challenged, stretched, or redefined. Once we believed the Earth was the center of everything. Once we believed time flowed the same for all observers. Once we believed atoms were indivisible. Each belief fell when confronted with deeper truth. Could the speed of light, the absolute horizon, also be one day overturned? Some physicists argue that it cannot, that the light speed barrier is as permanent as logic itself. Others suggest that under quantum gravity exceptions may appear. Space-time may not be continuous but granular, built of discrete units at the Planck scale. If so, then perhaps loopholes exist, tiny cracks through which faster-than-light travel might slip. Quantum entanglement already teases us with its strange instantaneous correlations, though no information can yet be transmitted this way. Still, the hint remains. The universe may contain connections that ignore distance altogether. Even if these cracks exist, exploiting them may require energies beyond comprehension. To probe the Planck scale would mean colliding particles with powers trillions of times greater than our largest accelerators. For us it is impossible, but for a future civilization or for intelligence elsewhere, perhaps it is not. And if they can cross such thresholds, the horizons that confine us may be open to them. This possibility forces us to revisit one of the most persistent mysteries of our time, the silence of the cosmos. If advanced civilizations can reach the far side of the universe, or even leap between universes, why do we not see evidence of them? Where are the travelers, the signals, the artifacts? This is the Fermi paradox sharpened by our own dreams of cosmic travel. If the road exists, why does no one walk it? There are many possible answers. Perhaps the road does not exist and we are chasing illusions. Perhaps civilizations destroy themselves before they can attempt the journey. Or perhaps they do walk it, but in ways we cannot perceive. If wormholes or higher dimensions are their highways, their traffic may pass unseen. Their traces hidden in physics we do not yet understand. We may be like ants watching a superhighway, unable to recognize the vehicles that pass overhead. But another possibility is more unsettling. Maybe the silence is intentional. Perhaps advanced civilizations discover that horizons are not meant to be crossed. Perhaps they learn truths so dangerous that they retreat, choosing isolation over expansion. If the universe is structured to resist travel to its far side, then attempting to break those rules may unleash consequences that no intelligence is willing to risk. The absence of travelers may not be proof of impossibility, but proof of wisdom. Still, humanity is not wise in this way. We are restless. We test boundaries even when warned. We push forward even when failure is certain. That impulse has carried us from caves to continents, from Earth to the moon, from radio silence to signals spanning light years. It will carry us further still. Even if the other side of the universe is unreachable, we will try. And in trying, we will discover new truths as we always have. Every frontier humanity has faced has eventually fallen. Mountains have been climbed, oceans crossed, skies conquered. And even the moon has felt the imprint of our boots. Each time the impossible yielded to determination and discovery. But the cosmic horizon is unlike any frontier before. It is not a barrier of distance or danger, but of law. To cross it requires not more fuel or stronger ships, but new physics. And that raises an uncomfortable possibility. What if the laws are final? This possibility confronts us with humility. The universe may not be designed to accommodate travelers. It may not care about our longing to reach the far side. Our species may be confined forever to a local bubble, a cosmic village surrounded by walls of light and expansion. For some, this is a bleak vision, a cosmic prison that denies us our destiny. But for others, it is a call to look inward to find meaning, not in conquering horizons, but in understanding the space we already inhabit. Still, resignation does not come easily. Even if we cannot cross, we can learn. The universe may be vast beyond reach, but it is not beyond comprehension. Every photon captured by our telescopes, every ripple recorded by our detectors, every particle smashed in our colliders is a clue. Piece by piece, we reconstruct a picture of the whole. The far side becomes knowable even if it remains untouchable, and in this effort something remarkable happens. We begin to glimpse not just the structure of the cosmos but its story. We see how galaxies formed, how stars lived and died, how elements were forged in stellar furnaces. We trace the arc of cosmic history from the Big Bang to today. We even predict its future, imagining the heat death, or the big rip, the slow fade, or the violent end. The other side of the universe, then, is not merely a place. It is a narrative one that we are slowly learning to read, but knowledge does not erase mystery. For every answer, new questions appear. Why does dark energy exist? What is the true nature of time? Do dimensions beyond our perception shape the cosmos? Does the multiverse stretch infinitely with other realities pressing against our own? These are not idle speculations. They are the very questions that arise when we try to imagine what lies beyond our horizon. Perhaps the far side of the universe is not something to be travelled to, but something to be explained. Perhaps the true journey is intellectual, not physical. The act of asking the question forces us to develop new theories, new technologies, new ways of seeing. Already that impulse has given us relativity, quantum mechanics, and cosmology itself. Who knows what it will give us next? Still, we are human, and imagination will not rest. We dream of ships that ride the warp of space, of wormholes stabilized by exotic energy, of gateways to other universes. We dream because to stop dreaming is to stop being human, and maybe that dreaming itself is the bridge. We may never build the road with matter, but we build it with thought, with stories, with wonder. In this way, the unreachable far side is already shaping us. It compels us to push beyond limits, to wrestle with paradoxes, to embrace mysteries. It teaches us that horizons are not only obstacles but mirrors. They reflect our longing, our determination, our refusal to accept confinement. The other side may remain forever hidden, but in striving for it we become something more than what we were. To imagine the other side of the universe is to wrestle with paradox. On the one hand, physics insists that horizons are final, that light speed and expansion define what is possible. On the other hand, human curiosity refuses finality. We stand at the edge of what we can see, gazing into darkness, convinced that if there is a beyond, then one day we must reach it. This tension is not a weakness. It is the fire of discovery. We must remember that many boundaries once thought absolute have fallen. The sound barrier was once believed unbreakable. The energy required to leave Earth seemed impossible until rockets turned theory into reality. Even the atom, once considered indivisible, yielded secrets when we dared to probe deeper. Perhaps the cosmic horizon too will one day prove less absolute than it appears. But even if it does not, even if the horizon remains eternal, its existence gives us something of equal value. Perspective. By confronting our limits, we gain humility. We see how small we are compared to the cosmos, how brief our lives are compared to cosmic time, how fragile our planet is compared to infinite space. Yet humility does not diminish us. It sharpens our appreciation for the extraordinary fact that we exist at all. There is also irony here. The very limits that deny us travel to the far side are the same limits that allow us to be. If the speed of light were not finite, stars could not shine as they do. If dark energy did not exist, galaxies might never have formed in the balance we observe. The prison is also the nursery. The horizon that confines us is the same horizon that made us possible. Still we hunger for more. The question what lies beyond is not merely scientific, it is philosophical, even spiritual. It forces us to confront meaning itself. If the universe is infinite, then the other side is endless repetition, galaxies stretching without limit. If it is finite, then the other side may loop back upon itself, erasing the idea of edges altogether. And if there are multiverses, then the other side is not just different, it is alien beyond imagination. In each scenario, the message is the same. The cosmos is larger than us, larger than our hopes, larger than our fears. And yet it is also accessible through thought. Though our ships may never reach the far side, our minds already have. In equations, in models, in stories, we have crossed horizons many times. That act alone transforms the unreachable into something intimate, something that lives within us. Consider again the cosmic microwave background, that ancient wall of light. It is the farthest we can see, but it is also the closest we have ever come to the origin of time. From its faint ripples, we have deduced the age of the universe, its shape, its fate. In those patterns, the echo of the far side is already present. The universe may hide its edges, but it does not hide its story. It whispers it in radiation, in gravity, and the very elements of our bodies forged in ancient stars. The more we learn, the clearer the paradox becomes. The far side of the universe is unreachable, but it is not unknowable. It is forever beyond travel, but not beyond understanding. We cannot step across the horizon, but we can extend our minds beyond it. And perhaps that is the deeper journey. Not physical conquest, but intellectual transcendence. And yet a question lingers. What if knowledge is not enough? What if humanity demands more than understanding? What if we demand presence, contact, experience? Will we ever accept that some horizons are final? Or will we keep building theories and ships, always straining toward an ocean we cannot cross? We began with a simple but haunting question. Could we ever travel to the other side of the universe? Along the way, we encountered the speed of light, the expanding fabric of space, the mysteries of wormholes, the whispers of the quantum foam, and the silence of horizons. Each path offered possibility, and each path demanded a price too great for us to pay. The dream remains beyond our reach, but perhaps the true meaning of the question was never about arrival. It was always about the pursuit. The universe is not cruel, it is indifferent. Yet in that indifference lies wonder. For out of blind laws and cosmic forces, beings have emerged who can ask, who can dream, who can long for the impossible. We are creatures of limits, yet we imagine the limitless. That act alone changes everything. The horizon may confine our bodies, but it cannot confine our minds. As we reflect, we realize that the far side of the universe is not a place. It is a mirror. It shows us who we are when confronted with the unreachable. Do we surrender content with what is near? Or do we reach anyway, knowing we may never arrive? History tells us the answer. We reach always. Even when the stars were just points of light, we dreamed of touching them. Even when the oceans were endless, we set sail. Even when the atom was indivisible, we split it. Horizons inspire not by yielding, but by resisting. Perhaps then the greatest gift of the other side is not that it can be crossed, but that it cannot. Its refusal shapes us, pushing us to invent, to question, to imagine. In trying to reach it, we uncover new laws of physics, new visions of reality. In chasing it, we build telescopes that capture the faintest echoes of creation detectors, that hear the vibrations of space-time theories that reveal the hidden structure of existence. Every step forward, even without arrival, expands our universe within. Still we dare to wonder about futures we will not see. Perhaps in some distant age, minds far beyond ours will master dark energy, sculpt space-time, and tame the horizons. Perhaps they will cross into the far side, stepping into regions forever hidden from us. If so, they will carry with them not only their own ambitions, but our legacy. The first questions, the first attempts, the stubborn refusal to accept confinement. We are the beginning of that journey, even if we are not its end. And if no one ever crosses, if the far side remains eternally sealed, then it still serves its purpose. It teaches us humility, and wonder shows us the grandeur of what lies beyond reach, and reminds us that meaning is not found only in destinations. Meaning is found in the striving itself. So could we travel to the other side of the universe? The honest answer is no. Not with rockets, not with wormholes, not with any technology we can conceive. But could we imagine it, describe it, infer it, dream it? Yes, and in doing so we already cross a greater distance. The gulf between ignorance and knowledge, between silence and wonder. Let us then keep reaching. Let us keep asking, for the far side of the universe is not the end of our story. It is the beginning of our endless curiosity. And perhaps that curiosity itself is the true bridge, the one horizon we will never stop crossing. The universe is not eternal. At least not in the way we once imagined. For most of human history, we thought the heavens were fixed, eternal, unchanging, a silent backdrop to the drama of life on Earth. But modern science has uncovered a darker truth. The cosmos itself is mortal. Its brilliance is already fading, and in ways more dramatic than anyone could have foreseen. So here's the unthinkable question. Is the universe already dying? At first glance, the night sky offers no such clue. Stars sparkle, galaxies glow, supernovae erupt with dazzling power. From our vantage point, it all feels alive, vibrant, even eternal. But when we measure carefully, when we peer deeper with the most powerful telescopes, we see something else. Decline. Star formation is slowing. Galaxies are aging. Black holes are awakening in ways that drain the cosmos of its light. Join me today as we travel through time from the fiery birth of the cosmos to its inevitable demise. Along the way, we'll witness the rise and fall of galaxies, the treachery of black holes, and the slow suffocation of all that was ever bright. Our story begins in a paradox. The very forces that once gave life to the universe are now conspiring to extinguish it. The same gravity that gathered gas into galaxies now drags them into collisions that can strip away their future. The same black holes that regulate star formation can, if they feed too greedily, destroy entire galaxies from within. But here's the twist. The death of the universe is not a far-off event. It has already begun. Scientists now believe we live not in cosmic morning but in cosmic twilight, a time when the golden age of starbirth is already long gone, and what remains is only the long slow decline. How did the universe go from overflowing with new stars to slowly choking on its own silence? To answer that, we must travel back to its most glorious chapter, the peak of creation when the cosmos blazed with light as never before and never again. Cosmic noon. When the lights peaked, there was a time when the universe blazed. Astronomers call it cosmic noon, a turbulent era roughly 3 to 4 billion years after the Big Bang, when galaxies were ravenous and the sky was busy with birth. Gas streamed along invisible filaments of the cosmic web like rivers feeding a growing delta. Where those rivers met at the nodes, galaxies ignited. Back then, star formation was over 10 times the pace we see today. Entire neighborhoods lit up at once. Clouds collapsed by the thousands, turning cold hydrogen into furnaces of fusion. If you stood on an ancient world during that epoch and looked up, there would be more naked-eye stars than you could count. It was not a quiet universe. It was a construction site. But even at its height, the seeds of decline were being sown. The same inflows that fed young galaxies also triggered pressure waves, shocks, and winds. Starbursts bred supernovae, and supernovae bred feedback great outflows that heated gas and tossed it into the galactic halo where it could no longer cool and settle. Creation had a cost and the bill would come due. Meanwhile, collisions reshaped the landscape. Galaxies merged often, sometimes gently, sometimes catastrophically. In the most violent unions, gas clouds were compressed into a frenzy of starbirth, then blown apart by the very stars they created. Imagine a forest so fertile it grows itself into a wildfire. That was cosmic noon. And yet something even more decisive stirred at galactic centres. Supermassive black holes, quiet regulators, and calmer times woke to feed on streams of gas. Their accretion disks blazed across the spectrum, their jets drilled through entire galaxies. In moderation, they pruned growth. In excess, they sterilized it. Cosmic noon was glorious, but it was also self-poisoning. So why didn't this engine run forever? Because the universe doesn't just evolve in place, it expands. With every passing eon, the web-stretched densities fell and the fuel lines thinned. The banquet could not be sustained. How the cosmos learned to say no. To make a star, you need 3 things: gas, gravity, and time. To stop a star, you only need heat. Heat puffs gas up, keeps it buoyant, and denies gravity its grip. The universe discovered this trick early and used it everywhere. Start small. A newborn cluster breathes fire. Massive stars blast ultraviolet radiation and launch winds that sweep a nebula clean. Then they die, some within a few million years, with supernova shockwaves that punch cavities in the interstellar medium. Those holes connect, forming porous chimneys for hot gas to vent. The neighborhood cools more slowly. Fewer clouds collapse. Starbirth slows. Scale up. Entire galaxies surf on feedback. Starbursts launch galactic winds, vast outflows carrying metals and dust into the halo where they linger like heat haze. Cooling times lengthened. Gas that once fell readily to the disk now stalls in a warm suspension unable to condense. If the inflow weakens at the same time, say, because cosmic expansion starves the filaments, the galaxy's fuel tank drops below ignition. Then there's the black hole veto. Accretion flares heat gas not just locally but galactically. Radiation pressure shock cones and especially relativistic jets can inflate lobes of hot plasma tens of thousands of light years wide. That energy doesn't create stars, it prevents them, and the paradox deepens. The more massive the galaxy, the more massive the central black hole and the more decisive the shutdown. Dust, the quiet accomplice of star formation, plays both sides. It cools gas efficiently, enabling collapse. but when outflows drag dust into the halo, it becomes part of the insulation layer that keeps gas hot. The same grains that midwifed stars become the veil that delays their successors. Feedback isn't a switch, it's a thermostat with hysteresis. Once a galaxy gets too warm, it doesn't cool back quickly. The engine sputters, coughs, then idles. In extreme cases, it stalls altogether. Astronomers call it quenching a cold word for a hot process. So the great paradox arrives. The universe's most productive era built the very tools that ended it. Creation made its own breaks. Walk the morgues of the cosmos, the giant ellipticals, the massive spheroids, the silent graveyards of stars, and you see a pattern. Their colour has shifted from blue-white to red, a sign that short-lived high-mass stars vanished long ago. What remains are long-lived dwarfs flickering dimly along with the ashes of stellar evolution. White dwarfs, neutron stars, and the dark gravities of black holes. How did these cities of starlight die? Not by a single cause, but by a conspiracy. Repeated mergers choked their centres with gas until the central black hole lit up, sterilised the core, and drove the remaining fuel outward. Cluster environments stripped their reservoirs with ram pressure, a wind made of hot intracluster plasma that peels gas from a rushing galaxy. Others simply exhausted their supply and never got it back. Cosmic logistics failed. The strangest murders leave signatures. Jellyfish galaxies trail tendrils of star-forming knots, proof of stripping in action. Stellar streams arc across halos, fossils of swallowed companions. Radiolobes balloon from the core scars of ancient jets. In some, the disk remains, but it's empty of cold clouds. In others, even the disk is gone, replaced by a near-featureless ellipsoid. Not every galaxy dies young. Some, like our Milky Way, idle at a modest pace, turning a handful of suns per year. But patience is not a cure. The supply lines are thinning and our calendar is long. The cosmic actuarial tables do not lie. All galaxies will age into redness. Some will go quietly. Some will go with a last burst of fireworks. None will shine forever. And yet the autopsy offers more than grief. It offers a diagnosis. The universe is past its prime. That's not a metaphor, it's a measurement. The cosmic star formation rate peaked billions of years ago and has fallen ever since. We are witnesses not to the dawn of light, but to its long evening. If that's true, what comes after evening? Does the universe simply dim into sleep, or is there a deeper betrayal ahead? Dark energy. The expanding silence. Expansion was already the universe's plot twist. Accelerated expansion is its final act. In a cosmos driven by dark energy, space doesn't merely grow, it grows faster with time. Structures that are not gravitationally bound drift apart, redshifting each other into invisibility. The more the universe expands, the more capacity it has to expand. It's a feedback loop with no off switch. What does that mean for galaxies? It means supply chain failure at scale. The filaments that once funneled fresh gas into halos stretch thin. Inflows weaken. Star-forming disks sputter. Even without violent quenching, a galaxy starves. Think of civilization with empty roads. The cities still stand, but the caravans never arrive. On larger scales, dark energy redraws the map. Distant galaxies recede until their light is stretched beyond detectability. The cosmic microwave background continues to cool and fade. The ultimate baby picture becomes a ghost. In the far future, observers in our island group will see only their local-bound collection and nothing beyond. The universe will look small again, not because it is, but because the rest has slipped over a horizon of speed and time. Dark energy doesn't rip stars from galaxies. Gravity defends what is bound. But it does ensure that what's lost stays lost. No fresh gas from outside. No new mergers from afar. Only the long accounting of internal reserves. And once those are spent, there is no bailout. So the decline is double. Physics inside galaxies says heat the gas. Cosmology outside says thin the pipes. The combination is devastating, slow, inevitable, and almost polite. The universe dies not with a bang, but with a subsiding breath. But a whisper can carry. In the depths of time, do new wonders arise, rare sparks in the dark? The answer is stranger than it sounds. Long twilight. Embers that refuse to go out. Fast-living giants vanish first. It's the humble stars that inherit the future. Red dwarfs miserly with fuel can burn for trillions of years, far longer than the universe has currently existed. In the long twilight, they dominate the sky, faint but stubborn like coals that refuse to die. As metals accumulate, star formation itself changes character. Cooling becomes easier, the minimum viable star mass drops. Exotic outcomes appear at the margins. Barely there stars, glowing just above the threshold of fusion, their surfaces cold enough to host frost, their cores warm enough to sip hydrogen for ages. Where binaries of brown dwarfs collide, a true star can flicker on a match struck in an abandoned city. But every ledger balances. White dwarfs bleed their heat into space, sliding toward invisibility. Neutron stars spin down. Black holes feed rarely and quietly unless a stray passerby wanders too close. Entire planetary systems drift apart in slow gravitational pinball, ejected into the deep. The fireworks stop. The choreography continues. Against this hush, galaxies still act. The Milky Way and Andromeda merge, then merge again with their companions, forging a single island of stars. The local group becomes a local one, an oval of light floating in an expanding dark. Inside, the last cold clouds form the last modest generations of suns. Outside, silence accelerates. Is this the end? Not yet. Even after star formation ceases, physics remains inventive. Frozen iron hearts, possible exotic fusions, black hole whispers, each a new dialect of light. The universe does not give up easily. It changes the rules of its radiance. But change can be another word for diminishment. Every era illuminates less volume, fewer actors, narrower bands. The grand play becomes a monologue, then a murmur, then a breath. Black holes have always been the accountants of the cosmos, tallying mass and momentum with ruthless efficiency. In youth they regulated galaxies. In middle age they rationed fuel. In senescence they become the final collectors, sweeping up strays, swallowing the unbound, cashing out the last kinetic chips on the table. A quiet black hole is not asleep. It is patient. It waits for gravitational chaos to deliver it crumbs. A wandering dwarf star, a loose gas streamer, an unlucky planet. Each meal flashes a brief flare, then fades to infrared embers. Over absurd spans, central black holes grow even as their cities empty. But even the bookkeepers have a deadline. Quantum fields hum at horizons. Hawking radiation lets black holes leak. The bigger they are, the colder and slower the leak, but time is plentiful in a dying universe. Given enough zeros on the clock, every event horizon unravels. The ledger burns itself. After the last black hole evaporates, the universe enters a weirder quiet. No macroscopic engines, only particle whispers. Whatever complexity persists is held together by feeble forces over ridiculous distances. If there is meaning left, it sits in the statistics of noise. And yet if we've learned anything from cosmic history, it's that the universe surprises us. It found ways to ignite when it was thin. It found ways to regulate when it was crowded. Might it find ways to shimmer when it is almost empty? Physics hints at possibilities. Rare tunneling events, exotic condensates, improbable fusions in frozen matter. None make a new dawn. Some sketch a longer dusk. A future astronomer will see less, not because there is less to see, but because horizons move inward. The wider cosmos recedes beyond detectability. The fossil light of the Big Bang fades beyond inference. Without a cosmic backdrop, even the past becomes hard to prove. The universe will look provincial again, an island without charts. Does that mean truth disappears? Not quite. Physics leaves invariance relationships between things that do not rely on distant evidence. Gravity still curves space. Quantum fields still fluctuate. Thermodynamics still tallies loss. But the story grows incomplete. The archive goes dark. That is the final cruelty of a dying universe. It doesn't just dim the lights, it erases the records. Meaning survives where it can be remembered in structures that endure long enough to carry it. Stars once played that role, then planets, then minds. In the very long run, none are safe. So why tell this story now? Because we live in the brief, luminous window when the cosmos is both bright and knowable. We can see our origins, model our future, and understand the mechanisms that brought us here. Against a timeline of trillions, our moment is a spark. But it is also a summit. And there is a deeper consolation. Endings give shape to middles. The fact that the universe will die does not make it less magnificent. It makes it precious. The physics that writes the last chapter also wrote the first and everything we love in between. Echoes of the first light. Every ending hides its reflection in the beginning. To grasp how the universe fades, we must return to when it first ignited. For nearly 400,000 years after the Big Bang, there were no stars, no galaxies, only a seething plasma so hot that atoms could not exist. Photons ricocheted endlessly, trapped in an opaque fog. Darkness wasn't the absence of light. It was the imprisonment of it. Then came recombination. Electrons bound to nuclei atoms formed and photons were set free. That release still glows around us as the cosmic microwave background, a faint whisper stretched thin by billions of years of expansion. It was the first message, the first signal, the first memory the cosmos left us. But like everything else, it will fade. In 100 billion years, it will be too redshifted to detect. The first light will go dark. What followed was stranger still. The cosmic dark ages. Hydrogen and helium drifted in expanding space, cold and featureless. No stars lit the void. No galaxies stitched filaments together. If you could have stood in that abyss, you would have heard silence so profound it defies description. And then ignition. The first stars' titans of fusion erupted like beacons. They were nothing like the sun. They were hundreds of times its mass, blazing with ferocity, living fast and dying young. Their supernovae forged the first heavy elements, carbon, oxygen, iron, the raw ingredients for everything to come. But their brilliance was brief. Within a few million years, they were gone, leaving only black holes and enriched clouds behind. This was the universe's first betrayal. Creation inseparable from destruction. To make light, it had to ensure death. To seed planets, it had to burn through giants. Every gain was purchased in loss. If the universe began its story this way, sudden ignition, rapid death recycling into the next act, then perhaps its twilight is not a collapse but an echo. Not one death, but a rhythm of diminishing cycles. The question is, how many cycles remain? The rhythm of creation and decline. The universe breathes in waves. It does not simply expand, it pulses with eras. The age of first light gave way to the age of galaxies. The age of galaxies gave way to the age of clusters. Each epoch more complex, more structured, and paradoxically more fragile. At cosmic noon, the rhythm reached its crescendo. Galaxies collided, merged, and lit up. For a time, everything seemed to accelerate. More stars, more dust, more black holes feeding. But crescendos do not sustain. Energy disperses, heat accumulates, and order succumbs to entropy. In physics, it's not poetry, it's inevitability. Today we sit in a quieter measure. Star formation in the Milky Way produces only a handful of suns per year. Clusters that once blazed now drift into sedate equilibrium. The rhythm is slowing. Astronomers can graph it. A bell curve of starbirth peaking billions of years ago and declining ever since. We are living on the downward slope, and yet the cosmos resists silence. Even as the pace falls, creativity persists. Stars still form, galaxies still merge, black holes still flare. The universe is not dead, it is dying slowly. And that distinction matters because slow deaths leave room for strange surprises. But this rhythm has a grim conductor, entropy. Each transformation spreads energy. Thinner reduces its usefulness, makes the next act less likely. Entropy does not forbid complexity, it taxes it. Every star pays that tax. Every galaxy pays it, and eventually the whole universe will default. So the rhythm is more than history, it's prophecy. The arc from simplicity to brilliance to silence is not unique to life or planets or stars. It is cosmic law, which leaves us with a sobering thought. If the universe itself is subject to this rhythm, then perhaps everything we know is just one brief phrase in a song that is destined to fade. Entropy, the silent dictator. If there is a single law that writes the fate of the universe, it is entropy. Unlike the flamboyant forces of gravity or electromagnetism, entropy is quiet, patient, and absolute. It is the tendency of energy to spread, to equalize, to dilute its own usefulness. When a star shines, it is paying entropy's tax, turning ordered nuclear fuel into a haze of photons. When galaxies collide, they trade their neat orbits for chaotic ones. When black holes feed, they swallow information into horizons that may never return it. Each act of creation is also an act of surrender. On human scales, entropy looks like coffee cooling in a mug. On cosmic scales, it looks like the fading of starlight, the thinning of gas, the darkening of skies. Over trillions of years, entropy doesn't just win, it erases the scoreboard. The universe approaches thermal equilibrium where everything is the same lukewarm nothingness. No gradients, no flows, no engines, no life. This fate has a name. The heat death of the universe. It is not fire but frost, not explosion but stillness. Imagine a cosmos where every black hole is evaporated, every star has cooled, Every particle drifts alone in expanding space. Motion continues, but meaning disappears. Some physicists protest. Isn't this too simple, too final? Perhaps. Entropy is not destruction. It is redistribution. And sometimes redistribution allows new exotic orders to appear briefly. But entropy never forgets. It is the one account that never forgives debt. The cruelest part, heat death doesn't arrive in a sudden catastrophe. It creeps in increments, stars, dying galaxies, reddening horizons, slipping away until the silence is complete. By the time the end is obvious, it will already have been unfolding for eons. Alternate fates. Crunch, rip and bounce. The universe may be dying, but the manner of its death is still contested. Heat death is the front runner, but other candidates lurk at the edges of theory, dramatic, violent and strange. The Big Crunch imagines the universe reversing course. Expansion slows, halts and turns into collapse. Galaxies that drifted apart are dragged back together. Temperatures rise, densities soar. And in the final instant, the cosmos implodes into a singularity not unlike the one from which it was born. If true, then perhaps the Big Bang was not a beginning, but a heartbeat in a cycle of births and deaths. But so far, dark energy's acceleration makes this unlikely. The Big Rip is even more terrifying. If dark energy is not constant but grows stronger with time, it could eventually overpower even gravity itself. First galaxies dissolve, then stars are torn from planets, then planets are shredded into dust. Finally, even atoms are ripped apart as space-time itself fractures. The end arrives not in silence but in violence, a universe shredded down to its quantum threads. Then there is the Big Bounce, a phoenix scenario where contraction leads not to finality but to rebirth. Some models of quantum gravity suggest that the singularity of a crunch would rebound into a new expansion. If so, then our universe may be only one cycle in an endless chain. Every death would be a womb, every silence a pause before another crescendo. Each of these scenarios is speculative, but each carries a lesson. We do not know as much as we think. The cosmos hides its cards well. Our measurements today favour eternal expansion and heat death. But a subtle shift in dark energy's nature could flip the script entirely. So the universe confronts us with another paradox. The farther we look, the less certain the ending seems. Twilight has already begun. Look around our night sky. It feels vibrant, endless, eternal. But astronomers measuring the cosmic star formation rate know the truth. The universe's golden age ended billions of years ago. We are not in cosmic noon. We are not even in cosmic afternoon. We are in the evening. Our own Milky Way creates just a few stars each year. That may sound abundant, but compared to its past, it is meagre. 10 billion years ago, galaxies produced stars at a rate 10 times higher. Today, most galaxies are quiet suburbs rather than bustling cities. The light we see above us is largely the light of stars already burning, not the glow of new ones igniting. This is twilight, not metaphorical, but measurable. The decline is in progress. Cosmic surveys confirm that the universe is dimming. The proportion of blue star-forming galaxies shrinks. The red quiescent ones multiply. It is as if the universe itself has entered middle age, its vitality ebbing, its energy dispersing. And yet twilight has its beauty. The skies remain full, the constellations familiar. We exist in a rare window where the universe is both old enough to be understood and young enough to remain luminous. That balance will not last. Consciousness at twilight. Why do we exist now and not in some other era? Cosmologists call this the coincidence problem. Out of trillions of years, the universe may endure. Why are we alive during the brief sliver, when stars are still plentiful, galaxies still visible, and dark energy only just accelerating expansion? The answer may be selection. Life as we know it depends on the heavy elements forged in stars, but not too many generations in, or they would be locked in dead remnants. Civilizations require stable planetary systems, neither too chaotic nor too sterile. Consciousness blooms best in moderation between the violent dawn and the silent dusk. If that is true, then our existence is a mirror of the universe's own trajectory. We are children of twilight. We arose in the narrow band when the cosmos still burned brightly, but had cooled enough to craft planets, oceans, and DNA. In a very real sense, the universe had to age before it could know itself. But that awareness comes with weight. To know that the universe is dying is to feel a double mortality, our own and the cosmos's. And yet there is wonder too. For the first time in 13.8 billion years, the universe can look back at itself, measure its own decay, and write its own elegy. Reading the universe's medical charts, astronomers are physicians of the cosmos taking its vital signs. They measure redshifts to check expansion count star births to track metabolism, observe black holes to gauge stress. The charts are clear. The patient is stable but in irreversible decline. Deep field surveys with the Hubble Space Telescope and now the James Webb Space Telescope reveal the cosmic history of light. They show galaxies small and chaotic in youth, luminous in maturity and tired in age. Simulations like Illustrious TNG and Eagle recreate this arc with millions of virtual galaxies confirming the pattern. A steep rise in star formation, a peak, then a long tail of fading productivity. We can even quantify twilight. At cosmic noon, the universe formed stars at a rate over 10 solar masses per year per galaxy. Today the Milky Way manages just 1 or 2. In a trillion years, that number will be 0. The cosmos is not a patient that might recover. It is one moving predictably toward hospice care. But the charts reveal more than decline. They show causes, feedback loops, dark energy, environmental stripping, quasar activity, all written in the data. The universe is not dying of one disease. It is succumbing to a web of interconnected failures. In a way, it is not dying at all. It is simply completing its growth cycle. The black hole paradox. At the heart of nearly every galaxy lies a monster, a supermassive black hole. For years, they were thought to be passive, irrelevant specks compared to the galaxy around them. Now we know the opposite. They are the regulators of growth, the engines of decline, the paradox at the center of it all. When a black hole feeds it, unleashes more energy than billions of stars combined. This energy can sculpt galaxies heating and expelling gas-halting star formation for millions of years. And yet without them, galaxies might have burned their fuel too quickly, exhausting themselves even sooner. Black holes both prolong the cosmic dance and now terminate it. Observations of galaxies like M87 show the aftermath. Jets of radiation stretching thousands of light-years, lobes of plasma marking the crime scene of galactic death. The Event Horizon telescope captured its silhouette a black scar against infinity. It looked like the culprit caught in the act, the murder weapon still hot. So we face another irony. The very centers that gave galaxies their order are also the agents of their demise. Creation and destruction are not separate, they are entwined in the same engine. What does it mean for everything to end? It is one thing to chart decline, another to confront its meaning. If all galaxies fade, if all stars cool, if even black holes evaporate, then what remains? Does the universe end in silence, or does it transform into something beyond our comprehension? Entropy suggests finality, equilibrium, nothingness, no gradients left. But physics often surprises us. Out of plasma came atoms, out of atoms came stars, out of stars came life. At each stage, new forms emerge from apparent exhaustion. Could even the death of the universe hide seeds of novelty? Some theorists speculate about quantum tunneling events, vacuum decay, or exotic matter states that could give rise to new structures. Others dream of multiverse cycles, each death feeding the birth of another cosmos. But certainty eludes us. The best we can say is that the universe as we know it will end. Its familiar lights, its galaxies, its stars, its planets all will vanish. What remains afterward may not be the universe at all, but something unrecognizable. And yet perhaps that is enough. Knowing that even the cosmos is mortal reminds us of our own fragility, but also of our moment's magnificence. To exist in the brief era when the universe still shines is a gift no future epoch will hold. Earth under a fading sky. From our small blue planet, the decline of the universe is invisible. The sun still blazes, the Milky Way still arcs overhead. Telescopes still collect light from galaxies billions of years away, but every photon we catch is a message from the past, not the present. The farther we look, the younger the universe appears. The present-day cosmos is dimmer than any telescope can directly reveal. Earth itself is caught in a shorter countdown. In 5 billion years, the sun will swell into a red giant, scorching the planet and stripping away its oceans. Long before the heat death of the cosmos, our world will be uninhabitable. And yet Earth is part of the larger story. The fading of fuel, the aging of stars, the relentless arithmetic of entropy. Our night sky is a privilege of timing. Future civilizations, if any survive, will not see what we see. Galaxies beyond the local group will vanish into the accelerated expansion invisible forever. To them, the universe will look empty as if their island were the only one. They may never discover cosmology at all, so we live at a rare intersection, a habitable planet orbiting a stable star in a galaxy still active enough to study the cosmos while it is young. We are cosmic witnesses standing at the window of twilight. And the view is extraordinary. The longest goodbye, the future of the cosmos is not measured in centuries, millennia, or even millions of years. It is measured in trillions. In that vast calendar, entire civilizations rise and fall in the blink of an eye. Trillions of years from now, red dwarfs will still burn faint but steady. When they finally exhaust their hydrogen, they will fade into black dwarfs, cold embers in the dark. Occasionally, two brown dwarfs may collide, striking a brief new spark. But each flare is rarer than the last. After 10 to the power of 20 years, most stars are gone. Galaxies dissolve as gravitational encounters fling their stars into intergalactic exile. Black holes dominate the night-silent collectors of the last matter. Over still greater spans, even they evaporate via Hawking radiation, releasing faint whispers of heat until they too disappear. Beyond one Google years, the universe enters a new age, the dark era. No stars, no galaxies, no black holes, only particles drifting endlessly through a space that continues to expand. It is not violent, it is not sudden, it is the slowest, longest goodbye in history. Exotic endings. Physicists are not content with silence. They ask, could the end be stranger than we imagine? Some speculate about iron stars, hypothetical remnants formed when quantum tunneling allows protons in black dwarfs to fuse into iron. These stars would be dark, cold, and nearly eternal, glowing only faintly as they shed their last scraps of heat. Others point to vacuum decay, a catastrophic possibility rooted in quantum field theory. If our universe exists in a false vacuum, it could one day tunnel into a lower energy state. The transition would expand at nearly the speed of light, rewriting physics itself, obliterating all structure. No warning, no survivors, just a sudden change of rules. Then there are ideas even wilder. Boltzmann brains, self-aware fluctuations of matter arising from random quantum noise. If entropy rules forever, then given infinite time, consciousness might appear again by chance. But would that be life, or just the cruelest parody of it? Each scenario is speculative, but each shows the same truth. The cosmos is not guaranteed to die quietly. Its decline may hold surprises stranger than any beginning. Why knowing the end matters? If the universe is doomed, why should we care? Because endings give context to beginnings. Knowing the fate of the cosmos sharpens the meaning of our present. We are temporary, yes, but so is everything else. Galaxies, stars, and even space-time itself share in impermanence. To realize this is not despair, it is perspective. Our lives matter not because they last forever, but because they happen now in the thin, luminous band between chaos and silence. For scientists, studying cosmic death is not morbid curiosity. It is the continuation of a journey begun when humans first looked at the stars. For philosophers, it is a reminder that permanence is an illusion. For all of us, it is a call to wonder. In a universe destined for silence, we are the brief symphony of awareness. Full circle, the story of the universe begins and ends in darkness. At the dawn, there was a hot, dense fog, a silence waiting for stars. At the dusk, there will be a cold, thin emptiness, a silence after stars. Between those silences lies everything: galaxies, worlds, life and thought. In that span, light fought darkness. Hydrogen fused to helium, gravity sculpted suns. Chemistry gave birth to biology. Awareness arose, and for a fleeting moment the universe looked back at itself. That moment is ours. So is the universe already dying? Yes, the decline is measurable, inevitable, unstoppable. But death is not the opposite of life, it is its frame. Without it, nothing would matter. With it, everything becomes precious. When the final star cools and the last black hole evaporates, the universe will fall silent once more. But silence is not nothing. Silence is a canvas. Perhaps on it new symphonies may one day be painted. Or perhaps not. Either way, we were here in the brightness in the knowing. This is the story of the dying universe. A story still being written in starlight, and one we were fortunate enough to read before the ink fades forever. Dark matter, the invisible architect of decline. We speak often of stars, galaxies, and black holes, but the largest actor in this story is invisible. Dark matter. It outweighs visible matter by a factor of 5, binding galaxies in its silent grip. Without it, the Milky Way would have unraveled long ago. Yet in the long run, even dark matter cannot save the cosmos. Dark matter shaped the web of galaxies, sculpting the scaffolding on which everything luminous hangs. It guided the first clouds into collapse, seeded the first galaxies, and maintained their coherence. In that sense, it was the midwife of creation. But gravity is impartial. The same dark matter halos that once sheltered galaxies are now stretched thin by dark energy's expansion. Their role is less guardian, more undertaker. And there is a deeper mystery. We do not know what dark matter is. It may be a particle beyond the standard model or a shadow of something more profound. If it decays even slowly, then the universe's decline is not only inevitable but accelerated. In that scenario, the very skeleton of the cosmos crumbles. Imagine the irony. The invisible force that gave galaxies their strength might also dictate the terms of their extinction. If so, then cosmic death is not just written in starlight, but in the silence between stars. For billions of years, planets have been the quiet witnesses of cosmic drama. They orbit stars, cradle oceans, nurture atmospheres, and occasionally give rise to life. But what happens to planets in a universe that is running out of fuel? First they lose their suns. Stars like ours will swell, scorch, and shed their outer layers. Some planets will be engulfed, others will be cast into freezing exile. Around red dwarfs, worlds may endure for trillions of years, but their skies will dim as the stars themselves flicker out. Planets without stars wander the void, rogue worlds drifting in darkness. Some may carry subsurface oceans heated by radioactive decay, or tidal forces tiny pockets of warmth in an endless night. Could life persist there? Perhaps, but it would be a lonely persistence. Even the planets that remain bound to long-lived stars face slow decay. Tidal forces will drag moons into their hosts or fling them away. Atmospheres will leak into space. Over unimaginable spans, collisions will grind rocky worlds into rubble. Civilizations, if they endure long enough, will face stark choices. Abandon their planets for engineered habitats or find ways to harness dwindling starlight with impossible efficiency. And when the last star fades, even ingenuity may not be enough. Human beings once imagined the universe as eternal. To discover its mortality is both terrifying and liberating. If the cosmos itself will one day perish, then permanence is an illusion, and impermanence is the only constant. This realization has ancient echoes. Philosophers spoke of cycles of fire and rebirth, of worlds rising and falling. Modern cosmology confirms their intuition. Nothing lasts, not even galaxies, not even time itself. The scale is larger, the physics sharper, but the theme is the same. So what do we do with this knowledge? Some feel despair that all efforts are futile if the universe ends. But there is another view, that transience is what gives beauty its sharpness. A flower that never withers is scenery, not miracle. A star that never dies would never seed the chemistry of life. A universe that lived forever might never have birthed us at all. Seen this way, the death of the cosmos is not a tragedy. It is the frame that makes existence meaningful. Our moment matters not despite the end, but because of it. Humanity's cosmic diary. If the universe is destined to erase its own records, then memory becomes resistance. Every observation we make, every image from Hubble or James Webb, every equation written on a page is a diary entry against oblivion. We are the first beings, as far as we know, to measure the cosmos with such clarity. We have traced its birth in background radiation, mapped its growth in galaxies, and projected its death into trillions of years. In doing so, we have given the universe something it never had before: self-awareness. But how long will that awareness last? Our digital archives may not endure geological time, let alone cosmic time. Paper burns, servers corrode, even spacecraft decay. Perhaps our best hope is to scatter records across the stars, messages etched into durable media launched beyond the Milky Way, in the faint chance they survive longer than their makers. Even if no one ever reads them, these records matter. They are proof that for a brief era the universe knew itself. That knowledge is fragile, yes, but it is also luminous. Rebirth in the silence. Is death the end or a transformation? Cosmology does not answer, but it whispers possibilities. Some theories suggest that our universe is one bubble among many, and that when ours fades, another may ignite. Others propose cycles: expansion followed by contraction, collapse followed by rebound, a heartbeat across eternity. Still others hint at quantum fluctuations, where even in the emptiest dark new sparks may appear. We cannot prove these ideas. We may never prove them, but they remind us that the universe has always been stranger than expected. Who foresaw atoms in plasma, or galaxies in chaos, or life on a rocky world orbiting an average star? Perhaps the end is not final but fertile. Perhaps silence is not nothing but a canvas for another story. And even if that story never comes our own, was still written in stars, in minds, in memory. The universe is dying, but in its dying it has birthed the most improbable thing of all. Awareness that it is dying, and that awareness is ours. Life in the long night. When the stars fade, what becomes of life? For now we know it as fragile, bound to light and warmth. But in a darkening universe, the definition of survival must expand. Some speculate about civilizations around red dwarfs, tiny suns that can live for trillions of years. These stars burn so slowly that their planets may enjoy stability far longer than Earth ever will. If intelligence arises there, it may witness epochs beyond our comprehension. But even red dwarfs have an end. Other scenarios are stranger. Rogue planets with subsurface oceans could shelter microbial life warmed not by sunlight, but by internal heat. Could such life persist for billions, even trillions of years hidden in icy shells, while the galaxy outside grows silent? If so, life might never completely vanish, it would only retreat waiting in shadows. But intelligence demands energy. Civilizations need more than scraps of heat. They need power to think, to build, to dream. In the long night, energy becomes the rarest currency of all. The cosmos itself conspires against endurance, leaving the question open. Can life outlast its stars, or must it surrender to the annihilants? Dreaming beyond limits. Humanity has always resisted boundaries. Oceans, mountains, and skies were once barriers. Now they are pathways. But the limits written into the universe are different. They are not logistical, they are fundamental. The speed of light, the scarcity of fuel, the inevitability of entropy. These are not walls to climb, but laws to obey. Yet dreamers persist. Some imagine building Dyson spheres around stars, harvesting nearly all of their energy. Others imagine moving stars themselves, dragging suns into safe harbours to extend their lifetimes. In the far future, advanced civilizations might learn to tap exotic sources. Black holes, spin quantum fluctuations, or even the decay of dark matter. But here is the paradox. Every strategy still bows to entropy. Energy cannot be created without cost. At best, we can delay the inevitable. We cannot erase it. The universe is not a puzzle we can solve, but a stage we can perform upon until the lights dim. Still, perhaps that is enough. To live longer, to know more, to carry awareness farther into the abyss, this is not immortality, but it is defiance. And defiance too is meaning, the horizon of knowledge. Knowledge is light. It pushes back, darkness reveals patterns and tells us where we are. But knowledge, like light, has a horizon. In a universe that expands forever, that horizon creeps inward until much of reality slips beyond reach. Future astronomers will see fewer galaxies not because they vanish, but because their light will never arrive. The cosmic microwave background, our oldest record, will fade into nothingness. Even the fingerprints of expansion may grow too faint to measure. At some point, observers may conclude they live in a small, static cosmos. The truth will be gone not because it changed, but because it escaped observation. So there is a cruel irony. We alive today may be among the very few generations in all of cosmic history capable of knowing the universe's true story. We arrived at twilight, yes, but twilight is the moment when the horizon is widest, when the view is richest. We live in the golden hour of knowledge. But even now mysteries persist. Dark matter, dark energy, quantum gravity, our picture is incomplete. If knowledge has a horizon, perhaps we will never see the full portrait. And yet maybe that incompleteness is the point. Curiosity is not diminished by limits. It is defined by them, our place in a mortal cosmos. For thousands of years, humans wondered about the heavens. Now we know the heavens are mortal too. That knowledge is humbling, but it is also empowering, because it means the universe is not a cold, eternal backdrop. It is a partner in our story. We are stardust, yes, but we are also starlight, brief and brilliant. Our thoughts, our art, our questions, all are temporary flashes in a temporary cosmos. And that makes them more valuable, not less. What we do in our finite moment becomes our answer to the infinite. Civilizations may fall, worlds may perish, galaxies may fade. But the fact that awareness ever arose at all is a triumph against odds so immense they almost defy language. Even if the cosmos ends in silence, the song has already been sung. Perhaps our purpose is not to escape mortality, but to embrace it fully, to marvel, to understand, to record, and to love, knowing all the while that it will not last. That fragility is the source of beauty, the miracle of now. The universe is dying, the evidence is clear, the timeline inevitable. And yet look around. The stars still shine, the galaxies still wheel overhead, the Earth still hums with life. The miracle is not in what will happen trillions of years from now. The miracle is that we are here now, able to see it, to know it, to wonder at it. Mortality gives meaning to every sunrise, every discovery, every fleeting joy. A cosmos without death would also be a cosmos without urgency, without story, without us. The fact that it ends is the reason it matters. So let us not mourn the universe's fate. Let us marvel that in its vast unfolding there came a time when hydrogen burned into stars, stars forged heavier elements, planets formed, and one of those planets asked, what will become of it all? This is our moment. This is our window, and though the lights will one day go out, the wonder they inspired will remain for as long as we carry it, and perhaps beyond. The universe may end in silence, but in us for now it speaks. Epilogue, the elegy of immortal cosmos. The universe is vast beyond comprehension, yet fragile in its fate. For centuries humanity gazed at the stars, believing them eternal, believing the heavens to be the stage of gods or the machinery of forever. Today we know better. We know the cosmos is not timeless marble, but living fire, and like all fires it will burn down to embers. This knowledge is both humbling and electrifying. On one hand, it strips away illusions. There will be no infinite sky, no everlasting galaxy, no immortal suns. Every star will cool, every planet will freeze, every atom will drift apart. The great structures of the cosmos, spiral arms, clusters, filaments will collapse into silence. In time, even the black holes, those final sentinels of gravity, will evaporate into whispers of heat. On a long enough timeline, the universe becomes indistinguishable from nothing. On the other hand, this truth amplifies the significance of now. Consider the odds. 13.8 billion years of cosmic evolution, countless accidents and collisions, an immeasurable ballet of atoms, and in this fleeting moment, we are here. We can see galaxies at the edge of visibility. We can hear the echo of the Big Bang and microwave radiation. We can chart the future until the last light fades. We can know. That knowledge itself is a miracle. Think of what that means. Stars do not wonder if they will die. Black holes do not contemplate their own evaporation. But we do. In us, the cosmos has developed the rarest of faculties. The ability to reflect, to ask questions, to wrestle with inevitability. Awareness is not an escape from mortality. It is the flowering of it. Without death, awareness may never have existed. So perhaps the universe's ending is not tragedy, but culmination. It is the final chapter of a story that was always finite, always precious, always improbable. When the last star cools, the last photon fades, and the last black hole evaporates, there will remain only one undeniable fact. That once against all odds, the universe knew itself through us. And maybe that is enough. Maybe the meaning of a mortal cosmos is not to last forever, but to be noticed, to be understood, to be cherished while it burns. When future civilizations, if any endure, look back at this brief era of brightness, they may marvel that the universe ever achieved such clarity of self-reflection. For us, the lesson is simpler. Live as though every moment is as rare as a star, because it is. Every sunrise, every discovery, every act of wonder is a defiance of silence. We are the universe's way of celebrating its own fragile light. So when we ask, is the universe already dying? The answer is yes. But it is also still alive, still radiant, still telling its story in the language of starlight. We are part of that story. We are the witnesses, the recorders, the brief symphony before the long silence. One day silence will come, but today the stars still shine. And while they do so, do we?
What lies beyond the edge of the universe? Our observable universe, a sphere, some 93 billion light-years across, represents merely the fraction of the cosmos visible to our current technology, a limitation imposed by the speed of light and the universe's relentless expansion. But beyond this horizon, countless mysteries await, from the possibility of an infinite universe to the tantalizing concept of a multiverse. The questions surrounding our cosmic place continue to challenge our understanding of space-time and reality itself. Understanding these boundaries and the potential beyond is not just a scientific endeavor, but a journey into the very nature of existence, a quest that resonates with humanity's deepest curiosity and drive to explore the unknown. We stand at the precipice of the known, gazing into the vast, inky expanse of the cosmos. But how far can we truly see? The answer, surprisingly, isn't simply a matter of distance, but a complex interplay of light-time and the very fabric of space itself. Our vision is not unlimited. It's bounded by a horizon, an invisible barrier beyond which the universe remains hidden, at least for now. This boundary is not a physical wall, but rather a consequence of the finite speed of light and the expansion of the universe. Imagine shining a flashlight into a dense fog. You can see the beam for a certain distance, but beyond that, the light is scattered and absorbed, leaving the rest shrouded in mystery. Our observable universe functions similarly. Light from distant galaxies travels for billions of years to reach us, carrying with it precious information about the universe's past. However, the farther away a galaxy is, the longer its light has been traveling, and the farther that galaxy itself has receded due to the universe's expansion. This limit of our vision is what astronomers call the particle horizon. It's not a fixed distance, but rather a constantly expanding sphere, marking the edge of what is currently observable. According to current estimates, this sphere has a radius of approximately 46 billion light-years in every direction, giving our observable universe a diameter of roughly 93 billion light-years. Everything within this sphere, galaxies, stars, nebulae, and the faint afterglow of the Big Bang, is part of our current cosmic view. Beyond this boundary, however, lies the unseen universe. This doesn't mean that nothing exists there, but rather that the light from those regions hasn't had enough time to reach us. Galaxies could be forming stars, could be blazing, and potentially other structures or phenomena entirely alien to our current understanding may exist beyond the cosmic veil. The accelerating expansion of the universe, driven by dark energy, only deepens this mystery, pushing those distant regions further and further out of reach. This cosmic expansion isn't simply galaxies moving through space. Instead, space itself is stretching, carrying those galaxies away at an ever-increasing rate. Many galaxies are now receding from us faster than the speed of light, making their light forever unreachable. This is the cosmic event horizon, the ultimate boundary of what we can ever hope to observe. Therefore, defining the cosmic horizon isn't a simple matter of specifying a distance. It's about understanding the interplay of time-light and the dynamic nature of space in a universe constantly in motion. A universe that continually challenges us with its inherent mysteries beyond our current comprehension. Our everyday experience shapes our intuition about space. We live in houses with walls, cities with borders, and countries defined by lines on a map. It's natural then to imagine space itself as a kind of giant container, something that exists within something larger. But this intuitive understanding breaks down when we consider the universe at its grandest scale. According to our current understanding of physics, space isn't contained. It is the container. It's not something sitting inside a larger space. It's the very fabric of reality, the stage upon which the cosmic drama unfolds. Asking where space ends is akin to asking what lies north of the North Pole. The question itself is fundamentally flawed. The very concept of a boundary becomes meaningless when applied to the entirety of space. This isn't merely a philosophical point. It has profound implications for our understanding of the universe's structure. The idea of a finite universe with an edge implies a beyond a region outside of space itself. What would that even be? The absence of space. The absence of existence itself. These are questions that push the limits of our imagination and challenge the very foundations of our scientific models. Einstein's theory of general relativity revolutionized our understanding of space, revealing its dynamic and malleable nature. Space isn't a static background, but a flexible entity that can bend, warp, and curve under the influence of gravity and energy. The universe's shape, whether flat, spherical, or saddle-shaped, is determined by the distribution of matter and energy within it. This means that even the concept of straight lines becomes relative depending on the overall curvature of space. Therefore, to truly grasp the universe's vastness and mysteries, we must abandon our earthbound intuition of space as a contained entity. Space is the boundless arena of cosmic events, the dynamic medium through which galaxies move, stars are born, and the laws of physics govern the unfolding of the universe. It is not a vessel, but the very substance of reality itself. This fundamental shift in perspective is crucial for understanding the concepts we will explore throughout this journey. Whether the universe is infinite, extending endlessly in all directions, or finite yet unbounded, curving back upon itself in ways we can scarcely imagine, the very notion of a cosmic edge requires a complete re-evaluation of what we mean by space. The next section delves into the fascinating hypothesis of an infinite universe, a concept that challenges even our most sophisticated mathematical tools and stretches the limits of human comprehension. The concept of an infinite universe. A cosmos without boundaries, stretching endlessly in every direction, is both awe-inspiring and profoundly challenging to our intuition. Our everyday experience is firmly rooted in the finite. We encounter edges and limits everywhere we look. Yet the observable universe, vast as it is, offers tantalizing hints that might support this seemingly paradoxical idea. The uniformity of the cosmic microwave background, CMB. The faint afterglow of the Big Bang is one such hint. The CMB's remarkably consistent temperature across the entire observable sky suggests a universe that was once incredibly uniform and perhaps infinitely large. If the universe were finite, we might expect to see greater variations in temperature, reflecting the uneven distribution of matter and energy. However, the relative uniformity of the CMB has been interpreted by some scientists as suggesting a potentially infinite expanse. Of course, this is a matter of ongoing scientific debate. The observable universe only represents a fraction of the cosmos, limited by the finite speed of light and the universe's expansion. We can only see as far as light has had time to travel since the Big Bang. What lies beyond remains a profound enigma. However, the relative uniformity of the observable universe raises the interesting question of whether the patterns we observe extend indefinitely beyond our cosmic horizon. The implications of an infinite universe are profound. If space truly stretches on without end, then every possible arrangement of matter and energy given enough time and space would inevitably occur. This includes the possibility of countless copies of our own universe, even countless copies of ourselves, a concept that stretches the very notion of individuality and uniqueness. While this concept, often referred to as the Level 1 multiverse, raises profound philosophical questions, it remains a hypothesis, not an established fact. The infinite universe hypothesis, while not definitively proven, is a powerful and thought-provoking idea that continues to inspire scientists and philosophers alike. Its exploration necessitates a profound shift in perspective, requiring us to move beyond our human-scale intuitions about space and embrace the breathtaking possibility of a boundless cosmos. But it is crucial to remember, while the evidence supports the possibility of an infinite universe proving it definitively remains beyond our current observational capabilities. Imagine a being confined to the surface of a sphere, like an ant on a giant beach ball. No matter which direction the ant travels, it will never encounter an edge. The surface curves continuously, allowing for endless exploration without ever reaching a boundary. This seemingly paradoxical concept, finite size, no edge, is one model used to describe the universe itself. This model proposes a universe with a finite volume but no discernible boundary. It's not infinite in extent, possessing a definite, albeit potentially vast size. However, unlike the intuitive notion of a sphere with a clearly defined outer surface, this finite but unbounded universe lacks an edge where space simply ends. Instead, space curves back on itself in higher dimensions than we can directly perceive, creating a continuous, seamless whole. This concept is deeply rooted in Einstein's theory of general relativity, which describes space as a dynamic entity that can bend and warp under the influence of gravity and energy. The overall shape and curvature of the universe are dictated by the distribution of matter and energy within it. If the universe's density is precisely at a critical value, space would be flat. If it's slightly higher, space would curve inward like the surface of a sphere. If it's lower, it would curve outward like a saddle. The finite but unbounded model neatly avoids the philosophical conundrums associated with the idea of a beyond in an infinite universe. There is no outside to consider. However, it does introduce the intriguing question of the universe's overall volume. If the universe is finite, then what are the implications for the total amount of matter, energy, and information within it? Could it eventually reach a state of maximum entropy, a heat death that is both absolute and finite in scope? While the observed flatness of the universe, as suggested by measurements of the cosmic microwave background, CMB, initially favors an infinite model, this observed flatness doesn't definitively rule out a finite but unbounded universe that is simply too large to perceive its curvature in our current observational window. The ongoing quest to understand the universe's precise shape and size continues to be a critical area of cosmological research. This exploration of the universe's potential finitude leads us naturally to our next topic, the profound influence of Einstein's theory of general relativity on our understanding of cosmic geometry. Before Albert Einstein's theory of general relativity, space was largely considered a static, unchanging backdrop for the universe's events. Newtonian physics treated space as an absolute three-dimensional grid, providing a fixed framework within which objects moved. However, Einstein's revolutionary work fundamentally altered this understanding, revealing space as a dynamic and flexible entity. General relativity describes gravity not as a force, but as a curvature of space-time, a four-dimensional fabric encompassing both space and time. Massive objects warp the fabric of space-time around them, creating a gravity well that influences the motion of other objects. Imagine placing a bowling ball on a stretched rubber sheet. The ball creates a dip, and nearby marbles will roll towards it, mirroring how objects are drawn towards massive bodies due to gravitational effects. This curvature of spacetime has profound implications for our understanding of the universe's geometry. The overall shape and curvature of the universe, whether flat like a sheet of paper, spherical like a ball, or hyperbolic like a saddle, are determined by the distribution of matter and energy within it. This means that the geometry of the universe is not fixed, but rather evolves over time as the universe expands and the distribution of matter and energy changes. Measurements of the cosmic microwave background, CMB, the afterglow of the Big Bang, provide crucial information about the universe's overall geometry. The patterns observed in the CMB strongly suggest that the universe is remarkably flat on a large scale, although subtle curvatures are not ruled out. This flatness, in turn, informs our models of the universe's potential size and ultimate fate, an important factor in distinguishing between a finite and an infinite universe. General relativity's insights, therefore, are not merely mathematical abstractions, but critical tools in our ongoing quest to understand the universe's shape size and its ultimate destiny. The elegance and power of Einstein's theory remains central to our ongoing exploration of the cosmos. This understanding of space as a dynamic, malleable entity shaped by gravity and energy sets the stage for our exploration of the observable universe and its limitations. Next, we'll define the boundaries of what we can currently observe. Our understanding of the universe is fundamentally limited by the speed of light. Light, while incredibly fast, is not instantaneous. It takes time to travel across the vast cosmic distances, and this finite speed imposes a crucial boundary on our observations. This boundary, the edge of what we can currently see, is known as the observable universe. To comprehend this limit, consider the age of the universe. According to the prevailing cosmological model, the universe began with the Big Bang approximately 13.8 billion years ago. Since then, light has been traveling outward from the initial expansion, carrying information about the early universe. However, because the universe itself is expanding, this light has traveled a much greater distance than we might initially assume. The distance light has traveled since the Big Bang defines the furthest extent of our observable universe. This is not simply 13.8 billion light-years, because the universe has been expanding throughout this time. By the time the light from the most distant objects reaches us, those objects have receded further due to this continuous expansion. Current estimates place the edge of the observable universe at a radius of approximately 46 billion light-years, resulting in a diameter of roughly 93 billion light-years. This observable universe isn't a static entity. As time passes, light from increasingly distant regions eventually reaches us, expanding the observable sphere. Yet the universe's accelerating expansion, driven by dark energy, creates a countervailing effect. Galaxies beyond a certain distance recede from us faster than the speed of light, meaning their light will never reach Earth, regardless of how long we wait. This represents the cosmic event horizon, a boundary not just of current observability, but a fundamental limit on our potential future observations. This section helps us understand that the observable universe is not a fixed entity. Rather, it represents our current glimpse into a far greater and still largely unknown cosmos. Understanding this dynamic boundary is crucial to appreciating the challenges and possibilities inherent in exploring the universe's vast expanse. Next, we'll examine the concept of the particle horizon, a more precise definition of this observable limit. This brings us to a more precise definition of the boundary of our observable universe. The observable universe isn't just defined by distance, it's fundamentally constrained by the speed of light. This constraint, while seemingly simple, has profound implications for our understanding of cosmic scales and the limits of our observations. The particle horizon precisely defines this limit, representing the furthest distance from which light has had time to reach us since the Big Bang. Imagine the universe as a rapidly expanding balloon with galaxies scattered across its surface like dots. As the balloon inflates, the dots move farther apart. The light from each dot represents its history, its story told in photons. However, the light from more distant dots hasn't had enough time to reach us since the balloon started inflating. The particle horizon is like a circle drawn around a particular dot, us, on the balloon's surface. It encompasses all the dots whose light has reached that point. The particle horizon isn't a static boundary. It expands with time as more distant light finally reaches us. However, the universe's expansion isn't uniform. It's accelerating due to dark energy. This means the most distant galaxies are receding from us faster than the speed of light. This creates another more profound boundary, the cosmic event horizon. While the particle horizon represents the current limit of our observable universe, the cosmic event horizon represents the ultimate limit of what we will ever be able to observe, given the relentless acceleration of cosmic expansion. The particle horizon, therefore, is not merely a boundary of distance, but a boundary of time. It's the furthest point from which we can receive information from the past, a snapshot of the universe. At the moment those photons began their journey. This distance isn't fixed. It grows with time, but it constantly reminds us that our view of the cosmos is profoundly limited, a compelling reminder that the vast majority of the universe remains unseen, unexplored, and perhaps forever unknown. Understanding this light-speed boundary is critical to our ongoing efforts to map and interpret the universe's history and structure. This understanding of the particle horizon as a light-speed boundary naturally leads us to consider the profound implications of the universe's expansion. Let's explore how this expansion affects our understanding of cosmic boundaries. The discovery that the universe is not static but expanding revolutionized our understanding of cosmology. This expansion profoundly impacts our concept of cosmic boundaries, blurring the lines between what is observable and what remains beyond our reach. The very notion of a fixed edge to the universe becomes increasingly problematic in light of this continuous expansion. Imagine dots drawn on a balloon. As you inflate the balloon, the dots move farther apart, not because they are inherently moving, but because the space between them is expanding. Similarly, galaxies in the universe are not simply moving through space, but are being carried apart as space itself expands. This expansion isn't uniform. It's accelerating, driven by a mysterious force known as dark energy. This accelerating expansion has a significant effect on our ability to observe distant parts of the universe. While the particle horizon represents the current limit of what we can see, the accelerating expansion pushes galaxies beyond our reach, even those whose light has already begun its journey toward us. Many galaxies are receding so rapidly that their light will never reach us, no matter how powerful our telescopes become. This is the essence of the cosmic event horizon, the ultimate boundary of what we can ever hope to observe. Therefore, the expansion of the universe challenges our intuitive understanding of cosmic boundaries. The observable universe isn't a static sphere, but a dynamic, expanding region constantly evolving as light from ever more distant objects eventually reaches us. The accelerating expansion, however, fundamentally limits the information we can ever access, creating an uncrossable barrier beyond which lies the vast unknown. The universe's expansion, therefore, is not just a fact of cosmic history, but a defining characteristic of our ability to understand it, underscoring the immense scale and dynamism of the cosmos. To better grasp this concept, let's turn to a helpful analogy. The concept of a constantly expanding universe can be challenging to visualize. Our everyday experiences are grounded in a seemingly static world where objects maintain relatively fixed positions. To overcome this intuitive hurdle, let's employ a helpful analogy: the inflating balloon. Imagine a balloon with several dots drawn on its surface. These dots represent galaxies within the universe. Now, begin inflating the balloon. As the balloon expands, the dots move further apart. Crucially, the dots themselves aren't moving across the surface of the balloon. Rather, the surface itself is stretching, increasing the distance between all the points. This is analogous to the expansion of the universe. Galaxies aren't simply traveling through space. Instead, space itself is expanding, carrying the galaxies along with it. The distance between galaxies increases, not because they're actively moving away from each other, but because the fabric of space is stretching. The balloon analogy effectively illustrates this key concept. The surface of the balloon represents the three-dimensional space of the universe, while the dots represent galaxies. As the balloon inflates, representing the universe's expansion, the distance between the dots increases. However, this analogy has its limitations. The balloon is a two-dimensional surface, while our universe is three-dimensional. Also, the balloon has a defined outer boundary, while the universe, depending on prevailing models, may or may not. Nevertheless, the balloon analogy serves as a powerful tool for visualizing the expansion of space and how it impacts the distances between cosmic objects. This visualization helps to demystify the abstract concept of universal expansion, providing a tangible framework for understanding how our observable universe's limits are both dynamic and inherently restricted by the physics of light and space. This simple analogy illuminates a profound cosmic reality. This leads us to consider the profound philosophical implications of an infinite universe. If the universe is truly infinite, extending endlessly in all directions, the very concept of an outside becomes profoundly problematic. Our everyday experience is shaped by boundaries, the edge of a table, the horizon on Earth. We are accustomed to thinking of things as being inside or outside of something else. However, if the universe encompasses all of space, then the notion of something existing outside of it loses all meaning. Imagine trying to define what lies north of the North Pole. The question is nonsensical because the North Pole represents the furthest northern point. There's no further north to go. Similarly, if the universe is infinite, there's no outside because there's no further expanse beyond it. The universe in this context isn't a contained object within a larger entity. It is all of space encompassing all possible locations and directions. This challenges our intuitive understanding of space and existence. We naturally seek to understand our place within a larger framework, a container that provides context and meaning. But an infinite universe dismantles this framework. It presents a reality without boundaries, without an outside to define or contextualize our position within it. This doesn't diminish the universe's vastness or mystery. Rather, it elevates it to a level beyond our ordinary comprehension. The sheer scale and boundless extent of an infinite universe require us to reconsider the very questions we ask about its nature and our place within it. The question of what lies outside an infinite universe becomes not a question of physics, but of metaphysics, forcing us to confront profound philosophical questions about reality, existence, and the limitations of our human perspective. The concept of an outside in such a context may not be simply an unanswered question. It may in fact be a fundamentally unaskable one. This philosophical shift in perspective is crucial as we delve into the relativity of direction within the cosmos. Let's explore how our familiar notions of direction break down on a cosmic scale. On Earth, we have a readily available frame of reference for direction. We have a clear up and down defined by gravity. We have north and south determined by the Earth's magnetic poles, and east and west determined by its rotation. These directions are deeply ingrained in our everyday experiences. However, when we shift our perspective to the universe as a whole, these familiar concepts lose their absolute meaning. In the vast expanse of space, there is no universally defined up or down. Gravity acts locally, pulling objects towards massive bodies, but there is no overarching gravitational field to define a cosmic down. Similarly, the concepts of north, south, east, and west are rooted in the Earth's specific geometry and orientation. These terrestrial directions have no relevance in the context of the universe as a whole. Consider the Earth itself. On a large scale, it appears roughly spherical, yet for any given location, one can define up as the direction away from the planet's center. This direction changes completely depending on your position. This same principle extends to the cosmos. Any specific direction one points towards a distant galaxy, for example, is relative to our position and orientation within the universe. Therefore, the directionality we perceive is always contextual, contingent on our point of observation within the vast expanse of space. There's no objective universally applicable, up, down, north, south, east, or west, to guide us in navigating the cosmos. The concept of direction itself becomes inherently relative in the boundless arena of the universe. This fundamental relativity of direction challenges our anthropocentric view of the cosmos and requires us to embrace the immense scale and complexity of the universe. It is a profound aspect of cosmology that forces us to think beyond our human-centric frame of reference. This relativistic perspective is crucial as we attempt to quantify the immense distances involved. Quantifying the distance to the particle horizon. The boundary of our observable universe requires a nuanced understanding of both the age of the universe and the effects of its expansion. It's not a simple matter of multiplying the age of the universe approximately 13.8 billion years by the speed of light. The universe has been expanding throughout its history, and this expansion significantly alters the distances involved. The light we observe from the most distant galaxies began its journey billions of years ago, when those galaxies were much closer to us. As that light traveled, the universe continued to expand, increasing the distance between us and the source of that light. Therefore, the current distance to those galaxies is far greater than the distance the light itself has traveled. Astronomers use sophisticated techniques based on our understanding of redshift and the universe's expansion rate to calculate these distances. By measuring the redshift of distant galaxies, the stretching of their light waves due to the expansion of space, scientists can estimate how far away they are. However, these calculations are complex and depend on accurate models of the universe's expansion history, including the influence of dark energy. Current estimates place the particle horizon at a radius of approximately 46 billion light-years in every direction. This means that the diameter of our observable universe is roughly 93 billion light-years. It is important to emphasize that this is an estimate based on our current cosmological models and observational data. As our understanding of the universe improves, particularly our understanding of dark energy and the universe's expansion rate, this estimate may be refined. This vast distance, while mind-boggling, represents only the portion of the universe we can currently see. Beyond this boundary lies the vast unknown, a testament to the scale and mystery of the cosmos. It underscores the ongoing quest to better understand and measure the true extent of our universe. Having established the scale of the observable universe, let's now delve into its contents. Our observable universe, while vast, is not a uniform entity. It's a complex tapestry woven from a rich array of structures, each with its own unique characteristics and history. Mapping this cosmic tapestry requires a multifaceted approach, combining observations across the electromagnetic spectrum with sophisticated theoretical models. At the largest scales, The observable universe exhibits a remarkable large-scale structure. Galaxies aren't randomly distributed, but tend to cluster together, forming filaments and walls, separated by vast, relatively empty voids. These structures, revealed through extensive galaxy surveys, reflect the initial density fluctuations in the early universe, amplified by gravity over billions of years. The distribution of galaxies isn't uniform. Instead, it follows a complex web-like pattern, reflecting the universe's underlying gravitational structure. Within these galactic structures, we find individual galaxies, island universes of stars, gas dust, and dark matter. Galaxies come in various shapes and sizes, from spiral galaxies like our own Milky Way to elliptical galaxies and irregular galaxies. Each galaxy harbors billions or even trillions of stars, with its own unique properties and potential planetary systems. Observations of the cosmic microwave background, CMB, the afterglow of the Big Bang, reveal the universe's earliest moments, providing insights into the conditions that ultimately gave rise to the large-scale structures we observe today. Tiny temperature fluctuations in the CMB, detected by missions like WMAP and Planck, represent the seeds of these structures, the initial density variations that gravity amplified over cosmic time. Furthermore, the observable universe contains vast regions of intergalactic space, relatively empty voids, where matter is far less concentrated than within galaxy clusters. These voids are an integral part of the universe's large-scale structure, shaping the overall distribution of matter and influencing the evolution of galaxies. Mapping this complex interplay between galaxies, clusters, filaments, and voids requires sophisticated observational techniques and sophisticated theoretical modeling, demonstrating the immense complexity and breathtaking scale of the cosmos we inhabit. This intricate cosmic web, however, only tells part of the story. Let's now turn our attention to the echoes of the universe's earliest moments. This brings us to the cosmic microwave background. Peering deep into the cosmos, we can detect a faint, pervasive glow, the cosmic microwave background, CMB. This isn't starlight. It's the oldest light in the universe, a relic from a time just 380,000 years after the Big Bang. Before this time, the universe was a dense, hot plasma opaque to light. Photons couldn't travel freely. They constantly scattered off charged particles, preventing the formation of a clear image. As the universe expanded and cooled, however, it eventually reached a point where atoms could form. This crucial transition, known as recombination, allowed photons to decouple from matter and travel freely through space for the first time. This ancient light, stretched by the universe's subsequent expansion into the microwave portion of the electromagnetic spectrum, is the CMB. The CMB isn't uniform. It possesses subtle temperature variations across the sky, tiny hot and cold spots revealed by highly sensitive instruments like the WMAP and Planck satellites. These minute temperature differences aren't random noise, but represent the seeds of the large-scale structures we observe in the universe today. The initial density fluctuations that gravity amplified over billions of years to create galaxies, galaxy clusters, and the cosmic web. By carefully analyzing these tiny variations in the CMB, astronomers can extract a wealth of information about the early universe. These measurements provide crucial constraints on cosmological models, including the universe's age composition and expansion rate. The CMB, therefore, is more than just a faint glow. It is a powerful window into the universe's infancy, offering valuable clues about its origins and evolution. It's a cosmic time capsule preserving the echoes of the Big Bang and providing a foundation for our ongoing efforts to understand the universe's history and structure. The CMB is a fundamental element in our understanding of cosmology, a direct link to the very beginning. However, even the CMB has its limitations, leaving us with many unanswered questions about what lies beyond our current observational capabilities. Let's explore some of these intriguing possibilities. The limitations of our observational capabilities imposed by the speed of light and the expansion of the universe leave a vast expanse of the cosmos shrouded in mystery. While we can observe a sphere roughly 93 billion light-years in diameter, what lies beyond this particle horizon remains largely unknown, fueling a wealth of intriguing speculation. One possibility, of course, is that the universe extends infinitely beyond our observable region. If this is the case, then the structures and phenomena we observe within our cosmic horizon, galaxies, stars, and the cosmic web likely continue indefinitely extending far beyond our current observational reach. This infinite expanse could potentially contain countless other galaxies, stars, and potentially even civilizations beyond our current ability to detect. Another possibility is that the universe, while not infinite, is far larger than our observable universe. This beyond might contain structures and regions that differ significantly from what we observe, perhaps with different physical laws or distributions of matter and energy. The uniformity of the observable universe, as suggested by the CMB, might not extend to these far-off regions, creating a universe vastly more complex than we currently imagine. Further adding to the mystery is the concept of the multiverse, the idea that our universe is just one among many, perhaps even infinitely many. These other universes could exist in separate regions of space-time, perhaps even with different physical laws or fundamental constants. Our universe in this view might be just one bubble in a much larger cosmic foam. Finally, we can't discount the possibility of unexpected phenomena beyond our observational limits. Perhaps forms of matter or energy that are currently unknown to us exist in these unseen regions, governed by laws of physics we haven't yet formulated. The universe beyond the horizon could hold surprises far beyond our current expectations, pushing the boundaries of scientific understanding. These are merely some of the myriad possibilities, all subject to ongoing scientific investigation and debate. The exploration of the universe beyond the horizon remains a compelling frontier of scientific endeavor. This leads us to another crucial aspect of modern cosmology, the accelerating expansion of the universe. Let's examine the implications of this discovery. For decades, astronomers assumed that the universe's expansion, first discovered by Edwin Hubble, was gradually slowing down. Gravity, after all, is an attractive force, and it seemed logical that it would eventually counteract the outward push of expansion. However, observations made in the late 1990s using distant supernovae as standard candles to measure cosmic distances revealed a stunning reality. The universe's expansion is not slowing down, it's accelerating. This unexpected discovery, which earned several scientists the Nobel Prize, introduced a new enigma into cosmology: dark energy. This mysterious force, seemingly permeating all of space, acts as a kind of anti-gravity pushing the universe apart at an ever-increasing rate. While we don't yet fully understand the nature of dark energy, its effects are profound and far-reaching. The accelerating expansion significantly alters our perspective on the universe's past, present, and future. It affects the observable universe's boundaries, creating the cosmic event horizon, a limit beyond which events can never affect us regardless of how long we wait. Galaxies beyond this horizon are receding from us faster than the speed of light, their light forever lost to our observation. The accelerating expansion also has implications for the universe's ultimate fate. While various scenarios are possible, the accelerating expansion suggests a universe that will continue to expand indefinitely, growing ever colder, darker, and emptier a big freeze scenario. However, alternative models remain viable, highlighting the ongoing nature of scientific inquiry. The implications of the accelerating universe are not only cosmological, but fundamentally alter our grasp of time-space and the very future of the cosmos, reminding us of the immense scale and unresolved mysteries of the universe. This accelerating expansion further emphasizes the limitations inherent in our observations, leading us to consider the concept of the cosmic event horizon. Let's explore this profound boundary. The accelerating expansion of the universe driven by dark energy creates a profound and irreversible boundary, the cosmic event horizon. This isn't merely a limit on our current observational capabilities, like the particle horizon. It's a fundamental limit on what we can ever observe, a one-way street in spacetime. Imagine a galaxy far, far away. Light from that galaxy is traveling towards us, carrying information about its past. However, because the universe's expansion is accelerating, that galaxy is receding from us at an ever-increasing rate. Beyond a certain distance, the cosmic event horizon, the galaxy's recession speed surpasses the speed of light. This doesn't violate Einstein's theory of relativity, because it's not the galaxy itself moving faster than light through space. It's space itself stretching, carrying the galaxy beyond our observational reach. This means that light emitted from beyond the cosmic event horizon will never reach us. No matter how powerful our telescopes become, or how long we wait, those galaxies will remain forever hidden from view. This isn't just a matter of technological limitations. It's a fundamental constraint imposed by the physics of an accelerating universe. The cosmic event horizon represents an absolute boundary, a point of no return in our cosmic journey. The implications of the cosmic event horizon are profound. It challenges our understanding of causality, suggesting that events beyond this boundary can never have any influence on our observable universe. It also raises questions about the ultimate fate of the cosmos. In scenarios where the expansion continues to accelerate, increasingly larger portions of the universe will slip beyond our event horizon, ultimately leaving us isolated within a shrinking observable sphere. The cosmic event horizon is a stark reminder of the universe's immensity and the inherent limitations of our perspective within this vast and ever-expanding cosmos. It's a boundary not merely of distance, but of time and causality itself. This inherent limitation in our observations underscores the importance of understanding the constraints imposed by the speed of light and the age of the universe.